Ja. Hello, test, test. Oh no,
Yeah.
this not even works. Wait, right, sorry, you wait.
So we're really pleased today to be introducing this pod here at HKUST, and we've got a very lively agenda that we're sharing locally, but also live streaming to the world. We're going to kick off today with this welcome, and then have a brief skim through all of the papers that have been published at this year's NINES, and we'll have the opportunity for all of the people physically here, but also all of the people online, to vote for which papers that we discuss. We're also really lucky that we're joined by Hong, who will be giving a keynote at 11 a.m. Hong Kong time. Afterwards, we'll have a lunch break, and then after the lunch break, we're going to have a mini presentation setting where we've got a bunch of students and staff who are going to give very brief introductions to their work and hopefully trigger some lively discussion. After that, we're going to have another couple of presentation sessions where we're going to be playing out the NINES content. And then for the people who are physically here, afterwards, we're going to have a nice social event in the evening where we go for some drinks. So there was a really eclectic bunch of interesting papers submitted to NINES, as I'm sure all of the other pods have recognised. We've grouped them into 5 different categories, and what I'm going to first do is skim through them so that afterwards, when we do the voting, people have an idea of which papers they're picking. So we have a number of papers in the programme that are focusing on the fundamental nuts and bolts of the architecture of the internet, including things like design principles. And you can quickly skim your eyes over the content and try to remember which ones look most interesting to you, because afterwards we're then going to do the vote. So you can see from the titles the types of topics that we're covering. We've got some really interesting work looking at the fundamentals of things like packet routing and the economic impacts of packet routing. Also, I think this looks like a really interesting paper I'm going to vote for, looking at some of the changing internet architecture concepts and perspectives on that. And I'll hold this up for just one more minute so people can take a look and pick which papers they might want to vote for, before moving on to the next topic, which is congestion control. Again, we have 6 papers listed here, all of which are focusing on congestion control, transport, and management issues within networks. So again, I'm going to leave it for a moment so you can take a glance and spot which papers you find most interesting. But I think what's interesting here is we have some conceptual papers looking at some of like the real nuts and bolts and building blocks of how congestion control works, but also some algorithmic suggestions as well as how we can do it differently. So if you have time to look at the titles and make their decisions. So the next group of papers in the programme are looking more at distributed systems aspects. So there are a bunch of contributions here where the authors have proposed alternative ways of building systems to deliver some very cool features in the network. So probably some of these buzzwords you can already recognise, such as looking at CDN replica selection and distributed clocks. So again, I'll just leave this up for a couple of moments so people can look at the titles and perhaps think about which ones they'd be most curious to hear. Before we move on to space, C, and NTNs. So anybody who's been keeping an eye on the networking world recently would have noticed that there's been a flurry of interest in things like LEOs, and that was reflected in the NINES submission. So there were lots of papers proposing really cool ideas about how we can build and improve space, C, and NTN networks. So I'll leave this up for a moment. Right. Next, as always, in the SIGCOMM community, we have some really nice submissions on security as well. So these tended to be looking at new security vulnerabilities and also questioning some of the principles of how existing systems work and how we can better improve the security. This is going across like our traditional networks, looking at things like BGP hijacking, a topic which I guess most of you are already very familiar on, but also some innovations within specific security architectures like Tor. So this paper was introducing some concepts related to services running in Tor and how to make them more secure from attack. So just leave that for a moment so you can jot down which ones you're more interested in. Then last but not least, the final set of papers is focused more on mobile and wireless computing. And as you can see, there are some nice papers looking at comms issues such as 5G RAN and also Wi-Fi networking and things related to like disaster recovery. Okay, so now everybody's hopefully jotted down which ones from that they're interested in. That brings us to the end of the main track of papers, but one of the really cool things that the NINES program put together were some interviews. So there was an interview with Jennifer Rexford and also Tinder from Google. And you can see who they were conducted by, and personally I think this is a must. I think you have to watch these because I think they're going to be really interesting content. Okay, so we've just covered all of the papers within the program, and now we have the exciting interactive part of the session where we get to vote. So we have a QR code up here. All of you should be able to scan this using your chosen app, and it will take you to the Mentimeter page. And the Mentimeter page is going to allow you to click which papers you're most curious about. And the ones that get the most votes will be the ones that we watch in today's sessions. So, we already have one vote. Clearly, people are very excited here. So as we step through, you'll notice that your page changes and you'll have the different options available to you. You simply click the ones that you want, and it could be multiple. And then at the bottom, you'll see there's a submit button, and that will register interest. So I'm also going to be voting here. So we have some winners emerging here, I think. What we're going to do is run the session based on discussion. So people are discussing a paper. We're not going to kill the discussions. We'll just run through as many presentations as we can. But the focus really on is the discussion part. We're going to discuss for half an hour. We'll view fewer presentations. Okay, so has everybody voted? Anybody need some extra time? Oh, there's always one. So you work at Science and Technology University, right? You sure? Yeah. Okay, so that was the vote for the Internet Architecture set of papers. You probably remember the next one was the congestion controlled transport and traffic management papers. So hopefully all of your pages have changed on Mentimeter, and again you'll be able to vote. It's interesting that. Okay, so it's good. So it's good. What is it? Some kind of doesn't matter. Just curious. This is a fantastic question, and one that I'm going to take offline. Okay, great stuff. Good votes. On to the next topic. You might remember the distributed systems, security, and infrastructure. So hopefully your page has changed again. Okay, so we have some. Oh, we have 2 winners. Oh, 3 winners. Oh gosh, okay, somebody just pushed the CDM paper into the lead. Good choice. Any final votes? Okay, Space C and NTNs. I think this one is going to get a lot of interest. Orbital brain leading, followed by monitoring latency. Oh, monitoring latency takes the lead. Great stuff. Any extra time needed? Everybody okay?
Yep.
Okay. On to security. 4 papers to pick from here. I'll pretend I didn't hear it. Yeah. Okay, so we have a clear winner here.
This is one of you.
Okay, and our last set of papers to pick from, the wireless and mobile. So again, hopefully your page has changed and you can see these 4 options.
Right.
Okay, I think we have a clear winner here. A very clear winner. Okay.
It's not one way. I just keep going.
And last but not least, we have the 2 interviews that I mentioned right at the end.
Oh, okay.
So I'm definitely voting for both. Okay. Any final votes coming through?
Really doesn't print the name.
Yes.
Interactions.
In the interest of full transparent disclosure, I am not receiving any funding or money. So okay, wonderful stuff. So, given that we now have the voting in, we can switch across to the actual presentation. So, just to remind folks of the agenda, we're going to kick off with about an hour slot of the video presentation before we move over to our keynote speaker. And what I propose we do is go through the sessions one at a time so that we've got like a general grouping of themes. So I'm going to propose we start off with the internet architecture theme. And for that reason, I'm going to stop sharing and jump onto this computer. Okay, interesting. Let me see if it's the. Yep, it's interesting. Does it work? Yeah. Did that doesn't work? I think maybe this is excluding. Oh, what is that? So I think it's fine for them. It's just 11617 97255 972. Hello, my name is Stuart Cat.
As a part of this conference on new ideas and network systems, the organizers asked people to give talks on where the field might go in the future. This is an informal talk, and my goal is to stimulate discussion. I hope I can say something stimulating, but not controversial. We're going to talk about two topics in this talk. And for the first one, I need to go back in time. I'll go back to the first outrageous opinion session at CCON. I gave a talk that was titled, "We Should All Become Economists." I'm going to revisit that idea. I want to tell you two stories, personal stories about the 1990s. And those of you who know me, you may have heard these stories before because I've told them many times because they were so important in shaping my own thinking in the 90s. The first story, I was talking to an economist who really understood the internet, and he said, the internet's about routing money, and routing packets is a side effect, and you screw up the money routing protocols. And I said, I didn't design any money routing protocols. He said, that's what I said. Second conversation involved the CTO of a major ISP. In the 1990s, we were working on service stuff. We got DipServe, we got DipServe, all this kind of cool stuff. And I went to this guy and said, this is really fun, you should turn it on. He said, no. Just clear answer to what I expected. I said, why not? He said, why should I spend a lot of money to turn on quality service so Bill Gates can make a lot of money selling internet telephony for Windows? I said, wow. Yes, there's a money insulator between the IP layer and the apps. And in fact, it's a good thing. We liked it. It meant that the apps couldn't, ISPs couldn't try to monetize the apps, and the apps couldn't try to monetize the ISPs. But it also meant that there was no reward from an ISP and consumer service. So what I learned in that decade is that the shape of the future is defined by money and investment. It's not just defined by technical innovation. But more specifically, why do I care about money routing? I care about money routing because I care about the possibility of having systems in the internet that are decentralized. Why do we want to have decentralized systems? Or sometimes people say ecosystems. It's not just that lots of people can make money. System design, or particular system modularity, is allocation of power. I don't mean electricity, I mean the ability to shape or control what others do. Decentralized systems diffuse power. Systems under centralized control concentrate power. That's what we see with Facebook and Google, etc. I'm worried a lot about the current concentration of power in those large and well-funded actors. Systems under decentralized control are one counterforce. The counterforce, of course, is regulation, but we're not doing very well with that. These actors are global in scope. But for decentralized ecosystems to be viable and stable, the participants in the ecosystem must understand how they can cover costs and make money. Let's look at a couple of examples of decentralized systems. The first and obvious one is the internet itself. The internet is under decentralized control. There are about 77,000 interconnected autonomous systems. ISPs have some norms that define how they interconnect. That is the money routing model. We have transit, we have revenue neutral period. But we've seen these norms break down, as in the dispute about 10 years ago between the ISPs and the content providers. The ISP set for Comcast as the champion, the content providers set for Netflix as their champion, and they did battle. And the dispute between the two of them got so bad that the parties actually went to the FCC to state their respective cases. And they got before the challenger FCC, who said to them, wait a minute, did you really come here and ask the FCC to set interconnection tariffing on the internet? I call it money route, right? And they said, oh my God, that's not what you meant. They ran away. And it did get resolved, but painful. Here's another example of a decentralized system on the internet that is stable, and that's the domain name system. There are lots of registries, there are lots of registrars, root servers, all these kind of things. Very decentralized. But the money route is defined by ICANN. And it's defined through the contracts that you sign if you want to be a registry or a registrar. So how much you have to pay and who you pay it to. So there's a centralized control of the money routing protocol. The IETF thinks it defines the protocols that define the investigating technical protocols, the money laundering protocols, central banking. And by and large, I think everybody thinks that, oh, I don't like the rules, I like them different because they don't need more money. But they're stable, predictable. They're stable, predictable, you can make money. Of course, the web is another decentralized system, and the economics of it is very simple. I pay for my part, you pay for your part. There's actually a name for that called bill and key. We actually can for yes, because there are other downstream bills. Today, the issues are not internet, the issues are arising at higher levels, the actor. That's where we see centralized actors with lots of power, Facebook. I'm going to teach about money routing, CS classes. I think maybe sure. I don't know many economists that think about this particular problem. Would be in the field of industrial organization. I think I'll say a little bit more about that before. We also don't teach about system modularity as the process of allocation of power across an ecosystem. In fact, we should teach that too. Sociologists and political scientists think about power. We do not think about systems design as a tool to control and allocate. So a lot of focus on RCA is centralized social networking apps. That's why there's a lot of interest in things like the Fediverse or the protocols of Blue Sky. But they fail to see they need a framework for money routing. Let's look at an example. Okay, I pointed out that the web is very simple because it's bill and key. Let's look at Blue Sky, as I mentioned before. I don't know how much you know about the internal structure of Blue Sky. So let me put up the diagram here. On the left, you have a bunch of things called personal data stores. Now, actually, they both serve for posting and viewing, but in this picture, this is a flow of data, so the data is going from the left to the right. So the app posts something in the personal data store, and then there's this component called the relay. You see the relay up there, right? And the relay crawls over all the personal data stores and finds new stuff and produces output, which is called Firehose. And that output goes into something called the app view. And the app view, okay, this guy over here, right? This guy, the app view. That guy takes all of the information that's coming in about a particular post, because the post could be in one PDF and reply to the second PDF and reaction to the third PDF. It builds a complete model of each post, and then it produces the personalized feed for each user, which goes into their personal data store and see. Everybody pays for their own PDS, and there may be some true PDS as you can get. So in that respect, we will keep up. That relay up there, that relay that's up there, okay, and that actually those are expensive components. Who pays for it? Blue Sky is free. It's all open source. There's no advertising. Blue Sky was started by a philanthropist. It's a donation, but that was enough money, so we took some venture capital. Now I know it. I mean, we're not talking about a lot. But if you notice commercial from their venture capitalists to start generating a return. And they don't even know how to pay for the relay after. Okay. If Blue Sky struggles, it's going to be because they didn't have a good money routing model. Just for the fun of it, I might be worth looking at a different system. Let's talk about Signal, which is a very simple social networking app. There's no feed, there's no recommendation engine, there's no moderation. Okay. It's not under centralized control. Moxie Marlin's fight, the guy who started Signal, is working. More blog is worth going and finding. Decentralized systems cannot survive. Centralized systems will always win. So the only thing you can do is to try to make clear that you are benign dictator. So what did Signal do? It made several promises. It said, we will never profile you. We can't. That's what we do. We will never charge you money. How does it get paid for? It's a 501c3. It's a philanthropy. And the president of Signal, Meredith Wilbur, was wandering around the world trying to raise between $40 and $50 million a year to Signal. That doesn't scale. Where else can money come from? Advertising, yes. But that's what makes systems go evil. That's when they start profiling you, making you sticky, and trying to show you more and more ads. If you don't want advertising, there's only one obvious answer to the source of the money. And that it's going to be the users. It's going to flow from the edges. We're going to have to pay for the internet experience. And we should be going in that direction. But it's going to flow into the ecosystem in such a way that all people in there can make money. It's somewhat equitable. Like a lot of business, we don't create monopolies. So here's the next question. Where do money routing protocols come from? The IETF is very clear, at least it was a few years ago, they do not design business models. They don't want to touch this. But if nobody designs the money routing protocol, the centralized systems cannot survive. The next question, if somebody proposed a money routing protocol, why would the various actors in the system actually comply with it? Well, there are two answers. Okay, either the proposed solution has to be opposed, as it is with the centralized DNS model, but I can't say this is the answer. Okay, or it has to be system compatible. Now, I said a few economists look at the issue of money routing. There's one area with some interesting theoretical work called algorithmic mechanism design, AMD, or it's even more challenging variant called distributed algorithmic mechanism design, DAMD. This latter work derives from a framework optimizing social welfare, optimizing social value. The core idea of the area is a theorem by Arrow. It's a very limiting theorem by Guevara and Satellite. And there are ideas in here like different auctions and different mechanisms. I mention this only to lure those of you with a simple theory of the event to go exploring a little bit. There's a very clever paper Scott Schenker was authored together with Joe Feigenbaum and Michael Shapiro, titled Distributed Algorithm Mechanism Design. It's actually part of the book. It explains the idea, and it applies the idea to multicast routing and to BGP routing, which I thought was fascinating. However, I don't think that these ideas are general solutions in this area. Now, it may be the case that if a decentralized system is modularized in a particular way, it's easy or easier to argue that the proposed money routing scheme is insanely compatible. A lot of the work on designing financially stable decentralized systems has been done in the context of peer-to-peer networks like Bitcoin. This sort of system is comparatively straightforward. Everybody brings some resources, usually money doesn't flow. The challenge there is to encourage the use of resources in a way that is consistent with what you brought. You're trying to damp or minimize free riding. And I think this could be my ignorance. I think this sort of reasoning is easiest to work through when the decentralized elements are somewhat homogeneous, like Bitcoin does. What you use should be in proportion to what you bring. And I don't know how much that idea generalizes either. I want to have one further thought in this space. If you look at something like a victory auction, and I know I haven't told you what it is, but that's okay. But it's models of one-shot games. They're good ones. In the internet, all the interactions are repeating games. And I think that imposes a very different kind of discipline on the behavior of the players. Actually, I have a further thought. I said this. I have a further thought. Blockchain is not the answer. Blockchain is a mechanism to move money. It's not the rules for how to move it. There's some complex reasoning about getting stable governance of the blockchain by the use of tokens. But I know of no scheme that maps tokenomics on the design of decentralized money routing protocols. That's the space of what is called decentralized autonomous organizations, DAOs. My understanding of the more defense into that space is that there are some issues there, and it's not clear that these ideas are generalized. So what's the bottom line? We need stable, predictable, incentive-compatible rules to get people to play. What does this have to do with packet routing? Perhaps nothing. If the focus of this conference turns out to be new ideas in packet routing, or new ideas in network technology, then what I'm saying can be ruled out honest. But if we want to contribute to the future shape of the internet, not just the packet carriage of the internet as an experience for buyers and users, I think we need to think broadly about what research and design will shape the future. I know this is far away from packet routing. Let me make it worse. Here's my second thought. To us, I'm talking about the typical people at a conference like this, the internet is a packet carriage where there's some apps on top. To users, packet carriage where there's invisible. To users, the internet is some apps with people on top. And if you want to understand what's happening in the internet space, we need to study people. We need to study why they do what they do. Let me give you just one simple example. Don't assume that they are us. Do not assume technical competence. I was talking to a security person, senior security person at Microsoft, who said, well, we just have to teach people how to look at a URL and tell whether it's malicious. No, that's stupid. That's the people who have no idea what a URL is to do something that we can't do for them. We have to make it easy for them. Let me give you some thoughts from psychology. I think that we should all become economists, and maybe we should all become psychologists and actually collaborating with behavior. Some of the psychologists now try to understand more about how people do what they do. There's an interesting thought from psychology. If you think about the experience of human interaction, okay, it has evolved rapidly. We grew up in tribes. There's some interesting research on named Dunbar, who's looked at different groups and he's talked to 5 very close friends, 15 sort of friends, and he said the most people can do to track of about 150 we grew up in tribes. Now we're shouting at the world, we're talking to 10,000 followers, 100,000 followers. The experience of interaction has evolved rapidly. The humans have not evolved, we still have a tribal brain. Okay. Now, we can cope intellectually, we can cope just fine. But there are some important lessons from brain science. Back in 2011, a man named Daniel Kahneman wrote a book called Thinking Fast and Slow. It was articulated in a model that was, at the time, a revolutionary framing of human cognition behavior. There's been a lot of research since then using functional MRI and things like that, and modern, more complex framing of what the brain is doing. But I think his language is still valid as a way to think about human behavior, and I like the language. The research he conducted established that the basis of human behavior is not entirely rational, simple as that. And people sometimes behave in reflexive and automatic ways. And that behavior was driven by what he called system one thinking. What he called system one test. It is, for example, the locus of the well-known fight or flight response set. And survival is the state of action matters. The time it takes to make a higher order decision would be the time it takes to die. So system one depends on heuristics, conscious habits, with second guessing. And system two, by contrast, is slow. It's deliberative, it's rational. System two is more complicated concepts like legality, morality, or calculation of possible outcomes of that. System two is slower, sometimes by far. System two can override system one. Sometimes in the second or two, and many of us can remember a moment when initial reaction to an event is replaced by a more studied reaction. The Kahneman describes system two cognitive processes as lazy. He did a lot of research. And what he pointed out is system two often doesn't bother to activate to reconsider system one decision. Now, let me put this in the context of computer system design. If you look at something like human-computer interaction research, their whole goal is to make things quick, simple, easy, and it's very efficient. Look what you can do is one click. You can like a post. You can forward, maybe that was incorrect information. Or you can follow a oops, I'm in a bad place, I just got spammed. Maybe we should slow things down. Maybe it's not always a good idea to make things as easy as possible. The benefit of slowing down certain actions arises from basic features about cognitive structure for trying to slow down so that system two can wake up and override the impulse of system one. There was a paper back in 2023, I think, by that freshman and Susan Garish, that argued that adding friction to certain actions would be important beneficial mitigation of bad behavior. Here's another lesson from psychology. The need to belong to, be accepted by a group is fundamental. The need to belong trumps other motivations, such as being truthful. Think about the flower of this society. I know people pretty decent flower workers and say, well, yeah, it's not fun, but there's so much fun to hang out with that other group. The most dangerous groups are groups that bring in outsiders and numbers. Think about people who can't actually deal with other people, and it gives them a sense of socialization and being radicalized. This is brainwashing. This is gaslighting. Okay? Group formation is truly something that's happening well above back and forth. So, do you have anything to do with that? You're going to offer a heretical idea, not advocate for it, advocate discussing it. In traditional groups, you have a strong social cue as to who the members are. With local groups, you may try to apply connections with some. You want to have strong signals about their important attributes so people habitually know who they are and who they are. Groups proposed to people with key clues about the identity and nature of the other participants may be the most at risk. This may be the most at risk of crafty manipulation. Very weak, very large groups also provide some psychological comfort to the most at risk. So perhaps group formation or communication in general with people far away that you haven't a clue about should include some additional steps we need to take. The techno-optimist vision of the internet is that if we built this global homogeneous infrastructure and everybody in the world talk to each other, wonderful, empowering things would happen. And it would, but at the same time, bad things would happen. Like scams, countries, state-level manipulation, social discourse, aversion, democracy. Perhaps when communications with people from distant parts of the world, there should be some friction. I don't think friction in this case means slowing things down after no seconds. No. It may require that communicants take additional steps. I think these steps may have to do with providing better cues about identity. I'm not saying your package should show passport from across the border, but the analogy is not totally wrong. If a teenage boy is being tempted by a sex extortion scam, perhaps it would help if the boy knew that the person he was talking to was an active like mine. I don't have time to say much about this topic, but I'll note that the question of how identity should be managed on the internet is a well-populated, contested area where different actors trying to accrue power by taking control. Right now, we see centralized control. Big tech is winning. Do you want your identity from Google, from Facebook? So once again, I do acknowledge I'm a long way from packet carriers, but I think it's useful to ask if the flow of packets should be shaped by concerns about things like privacy and accountability. Right now, there are strong insulators in the packet carriers layer and management of identity. When that kind of insulation can be sustained, it makes things much easier. But maybe it shouldn't be sustained. Now you'll say, what does this have to do with us? Our domain of research is moving packets. Should we allow ourselves to say that? Where is the action? Data center optimization, I'm going to be smart and say, are we really improving the world if what we do is improve the performance of systems that belong to the wealthiest firms in the world? Okay, should we just retreat to performance optimization? Are there services we should be designing that sit above packets and below apps? I said, by the way, a few years ago, the answer was blockchain, but I don't think that answer is quite as powerful now as it used to be. I think the IGF hates blockchains. But it is scary for someone else, either as individuals or as a field, I understand that. What constitutes publishable research? Will I get a job? Will I get tenure? Woo! The world is more mature. It's not the wide open spaces that I grew up in. Forget that. Can we change the world, or are we just putzing at the margin? Our dreams about changing the world, dreams from the past? We should at least have the courage to discuss that.
Awesome stuff. Thank our speaker. Any comments, questions, discussion?
Hello everyone. Today I'm so glad to be here to present our work.
So yeah, we have plenty of time to discuss today, so I don't know if anybody wants to share their thoughts on Dave's presentation.
I have kind of a follow-up presentation later, so yeah, it's good observations. Well, I think energy has been addressing topics for a while, and it's kind of the kind of knowledge that was gained from in this talk, so that initially people just felt uneasy with socialization, data exploitation, surveillance, and so on. And then there were some naive ideas of what you can do with blockchain and so on. And I think now the understanding has evolved a little bit into understanding a bit about control, power concentration. And so So if you want to do something about it, it's not enough to just pick some technical elements in the internet. So for the problem of NINeS, it's not only of security. And so even though then a few people out of the situation from very complicated to set up reliable, trustworthy services. So then use in the cloud because not only us, we are okay to do this large scale. I think we can fix that. We still have to fix the money problem. And so this is really quite enough. And even though the governments are also beginning to understand this, the needs that they have are also limited. So for example, if Europe decides some energy, that's a big tech regulation. So there's lots of counter pressure from other governments. But B, also what we have to say what are the right measures, right? So we have to do some maybe gradual change, so we have incentives for people to use maybe not using kind of apps. So it's really not an easy way to find a way out of this going to more and more convention. It's just currently not really easy. Yeah, so I think it's great and great talk. And then yeah, so we have some ideas, but so I think we have to, as Dave said, right, we have to do more than just thinking for the ideas and just more than just trying to fix some regulations. It's not that often a problem. But there are some of those architectural things. So, for example, it maybe easier for people to communicate directly. So that is getting the cross anchors. So that's going to be missing. That's going to be able to do it. We always have to go to everything. So there are some things we could do, but this is just like the foundation. So we have like platforms where people can use the apps and then people want to actually use these apps. And then if you use guys, for example, also you can have decentralized like other tools, but you also have to find ways to make this profitable, efficient, scalable, and so on. And like this way you can see that they have good ideas, but now they want to roll out their platform service, and they also want to make money or something. They tend to decentralize. So this architecture, but everything is one. So yeah, there are like two more questions. Money launching is certainly one important question. People are also not used to it. Pay for microservices, so it's really hard to set it up so that you can get to enterprise the phone service for people with normally social.
I mean, I think there are two principal problems. So the first is that most people would prefer to go for the fastest, easiest, cheapest option. And if that continues to be the centralized players, they will always pick that because from their standpoint, they don't care too much either way. So that drives consolidation because those centralized players accumulate more power, more wealth, and now compete in the big centralized alternatives. And the second one is that at the moment, we lack the nuts and bolts to actually decentralize anything because the way the internet architecture is built is through abstractions and cross dependencies. You know, when you build an application, you don't need to worry about naming because DNS can do that for you. When you build an application, you don't need to worry about congestion control because the transport layer can do that for you. But what then happens is that these cross dependencies mean that if you want to build something decentralized, it becomes incredibly difficult because many of the other nuts and bolts are centralized in nature. And I'm speaking today, for example, of decentralized social media apps like Fediverse and Bsky. This is a classic issue. So if you look at the hosting of this infrastructure, where is it? A lot of it sits on centralized cloud operators like Amazon. So you can build the coolest, most amazing decentralized protocol, but if its deployment is still dependent on centralized entities, ultimately it's still a centralized system. And it begs the question of whether or not it's even possible in reality to introduce these truly decentralized concepts when you have to depend at some point in the value chain on a centralized player.
And the other very challenging is that we certain stuff. Never learn about it. Let's say one website for one storage can install like, for example, I just got install on application. So this install download the EXE and install it on a laptop. Right? Also the piece of message.
You certainly can, but it begs the question of who built that application. Was it Adobe? Because I would argue that Adobe is probably a pretty big centralized player. And I think another problem is that the internet was initially designed with interoperability in mind. All the standards are there, everything's open, everything's documented, everything's been built. But going back to my first point, it's often just easier to reuse these existing central implementations, often commercial implementations, and by doing so, we just introduce yet another central dependency into the mix. I mean, even the internet itself, it's a decentralized protocol. It's got thousands and thousands of autonomous systems, but actually, if you look at the routing, it's highly dependent on a relatively small number of transit providers. And in some extreme cases, you have entire countries that have to route their packets outside of their own country elsewhere just to talk to the next door neighbor, which is crazy when you think about it. Yeah.
See right here, I send you a message on WhatsApp. You need to go through outside.
Exactly. Well, actually, Hong Kong was famous for fire chat. Remember this application back in 2014?
I mean, my teaching process.
Perfect. Yeah, that was a decentralized flagship application. Okay, so I mean, unless anybody else wants to chime in with thoughts, we could perhaps move on to one of the next presentations. No, we're going to go on to a paper presentation next, if that's okay by everybody.
Yeah.
So to the virtual audience, we've just switched the audio around, so hopefully you'll play out from the speaker. If there are problems, feel free to message on the chat and I'll try to fix it. So our next presentation is going to be Akio from Yale.
Hello everyone, my name is Anu Mohammad, and today I'm excited to present our paper, Axio Rethinking OS Architecture Co-Design for Next Generation I/O. This is joint work with my advisors, Professor Manohar and Professor Soleil at Yale University. So we love OS abstractions, but they are slow. In the recent years, we have seen a great performance improvement in I/O devices. We now have network devices that can support 800 gigabits per second and even more. Meanwhile, single-thread CPU performance has largely stagnated. We have reached the end of 10 scaling, and we do not expect to see much improvement in a per-core CPU performance anymore. As a result, the operating system abstractions that were designed decades ago with slow I/O devices in mind and were once low overhead are now sitting in the critical path of I/O. But what is the difference between these conventional abstractions and the high-performance ones that we have for I/O programming today? So here are the two ends of the I/O design space. On one side, we have the POSIX API that prioritizes ease of use. You can use POSIX and create a socket and use the system calls such as open, close, read and write, exactly like working with a file, to send and receive messages over the network. And by doing that, you let the OS handle device multiplexing, memory management, and header processing. On the other side, we have kernel bypass platforms such as DPDK that favor performance. In these systems, most complexity is pushed out of the kernel, out of the OS, and into the application. And the application developer has to now configure the device, set up the queues, and use polling APIs to receive messages from the network. Here, kernel is bypass. And this naturally raises a question. How different are these two abstractions, these two ends of the I/O design space in practice? So first, let's talk about the kernel-based network stack. Consider this system architecture that we have a NIC, we have a CPU and memory, and the CPU is running either on kernel mode or in user mode running an application. And the memory is divided between the kernel and the application. And now consider this simple example. This application that creates a socket and uses a read system call to receive data from the network. This system call will go to the kernel and will wait on the socket to get some data. And whenever the NIC receive a packet, it will do two things. It will first copy the packet into the kernel buffers, and it will fire an interrupt, letting the kernel know that the packet has arrived. And the kernel will then get the packet, processes its headers, finds the socket and application corresponding to the packet. It will copy the packet into the user memory and runs a context switch to give the control back to the application. And now the application can read the data. But what are the overheads here? And where is the time being spent? To figure this out, we ran a detailed breakdown experiment. It turns out from the time that the packet arrives at the NIC until it reaches the kernel, it accounts for 25% of the time. Roughly 15% of the time is spent on header processing in the kernel, and a significant 60% portion of the total latency is spent on context switching and copying from the kernel memory to application memory. So a lot of prior works have tried to optimize different components in this pipeline. One class of work would focus on using hardware accelerators and offloading engines to put more functionalities into the NIC instead of the OS. Another class of work would focus on optimizing the operating systems themselves by using techniques like zero copy IO. But the one approach that gives you the best performance is kernel bypass. And kernel bypass does that for us by giving direct access to the IO device to the applications. And by doing that, it basically eliminates two things in the breakdown that we had. It will eliminate user space delivery and header processing. And now we are only left with the time that the packet takes to travel between the NIC and the CPU. Kernel bypass has some limitations too. We need to put a lot of burden on the application developer. But what does it actually get you? What does kernel bypass buy you? To answer this question, we ran a simple ping pong experiment between two directly connected servers. This figure shows the distribution of round trip times, round trip latencies for applications written using DPDK and OS sockets. And we can see that DPDK applications achieve significantly lower latency compared to the OS sockets ones. However, this performance comes at a cost. And when we try to add back the features that are eliminated from the kernel, like multiplexing, we start to lose performance. We can see that we can lose 20% of the latency by adding a simple feature like multiplexing. And this raises an important question, that is there a fundamental trade-off between ease of use and performance, or can we have both? So we were wondering if we can get kernel bypass performance and POSIX APIs together. So to find an answer, we look to a successful precedent in computer systems, that is virtual memory. So virtual memory that has been evolving for more than 40 years now. It provides an abstraction that is both safe and high performance using a CPU memory and OS co-design. It gives the applications indirect memory access, but with the performance similar to a direct physical memory access. And it does that by introducing this hardware structure called TLB that caches page tables and translations, and the OS manages core data structures and the TLB. And our key insight is that virtual memory, in the common case, avoids the OS, avoids the kernel, but goes to the OS for exceptional cases. But how can we do the same thing for I/O? And this leads to our proposal, Axio, which is a novel software-hardware co-design that achieves high-performance I/O and preserves POSIX programming model. So prior works usually are reluctant to change the CPU. But we introduced small but important changes to the CPU microarchitecture and leverage the NIC hardware as an accelerator to offload header processing, transport protocol processing to it. And finally, we modified the OS to support our new features. So far we've discussed prior work and motivation behind Axio. Now let's look at the Axio design in more detail. Let's revisit the system architecture. We still have the NIC, the CPU, and memory with a clear separation between the kernel space and user space. First, we introduced two new things. First is a user space library that provides a POSIX-compatible API to our applications. Second, we leverage the NIC as a hardware accelerator and offload the transport protocol processing to it. So we basically do all the header processing in the NIC hardware and not the kernel anymore. Now, for connection setup, applications can use similar APIs like sockets to talk to Axio library and create a connection. And here, since we want our applications to have direct access, fast access to important informations about the connection, we introduce a new hardware structure called the IO connection table that holds very essential information about the connection and its associated process. This structure can be directly accessed from the application, but is mainly managed by the OS. So, and this looks like a TLB basically. And when a socket is created, the kernel will populate an entry about its connection and the process into the IO connection table. Now let's consider a read operation in Axio. So there are two cases for a read. We are either in a fast path or a slow path. So in the fast path, we assume we already have some data at the NIC that we want to read. So when the data arrives at our NICs, our modified NIC is able to communicate with IO connection table, letting it know that a new packet has arrived and get some information about it. And it will copy the packet directly to the application memory using those information. And after we issue a read command, our library will communicate with the IO connection table, understands a packet exists right now for us, so it will read it directly from the memory. And note that here, since we are not doing any system calls, we get exactly kernel bypass performance. But what happens if there's no data at the NIC already? In this case, we again call the read. Our library will talk to the IO connection table, but here we want it understands no packet has arrived. So in order to maintain the same blocking APIs as before, we have to suspend the application. So we go to the kernel, we ask the thread scheduler to do that for us. And here we want to have a way to actually let the application wake up immediately after a packet arrives. So we introduce another hardware structure called the IO ready queue that gets updated by both the thread scheduler and the IO connection table and acts as a cache for ready to run threads informations. So when a packet arrives at the NIC will again notify the IO connection table about it and will DMA the packet to the application memory. But now, since our application is suspended, it will also trigger an interrupt. And in the kernel, our thread scheduler will check with the IO ready queue, which is updated from IO connection table now, and understands that, okay, our application is able to wake up, and it will immediately do a context switch, give the control back to the application, and our application will eventually read the packet, read the data. And here we are using optimized interrupt delivery systems and hardware-assisted scheduling. And these two will allow us to have almost immediate wake-ups for our applications. But why do we need CPU changes here? So the core problem is that user space needs some information about the connection, but not full control. And because applications need to know if the data is available and where the RX and TX buffers are. At the same time, OS must control everything, and the NIC must be able to update these informations as well. And existing CPU abstractions just don't give us a clean way to do this. And this is the reason why we argue for modest changes to CPU microarchitecture. So the remaining question is whether this co-design actually delivers lower overhead and better performance in a real system. To answer this, we built a full hardware-software prototype and evaluated Axio. We integrated Axio into an open source RISC-V Rocket core and implemented both the NIC and the CPU on the same FPGA. Our Axio design consists of approximately 3,600 lines of chisel code, and it allows us to evaluate the complete system under realistic conditions. Note that our FPGA runs at 50 megahertz, and we only have a simple CPU microarchitecture. But a typical server runs at higher clock frequencies and has advanced CPU microarchitecture. So to account for these things, we scale our measurements in two ways. One is a 40x scaling based on clock frequency, and the second is a 200x scaling that also accounts for microarchitecture differences. And note that we only scale the execution time that occur on the FPGA. So if we send a packet and receive the response, we timestamp all the packets, and we only scale the regions that actually occur on the FPGA. And we now present our evaluation results. We begin with packet processing latency. We use a UDP ping pong benchmark for this, and we can see that at a 40x scaling, Axio achieves latency comparable to RDMA. In a realistic setting, we expect our performance to lie between these two curves of 40x and 200x, but we expect it to be more close to the 40x estimate. But overall, Axio improves latency by 31% compared to DPDK applications and also preserves POSIX API. Next, we evaluated throughput. We used the UDP workload for that, and we saw that Axio can saturate the FPGA bus bandwidth, which is lower than that of the modern servers, but still we expect Axio to saturate a 100 gigabit per second link in a realistic deployment. And finally, we examined CPU utilization using an Axio-based UDP server. We can see that actually we observed up to a 66% reduction in CPU usage compared to kernel bypass systems such as DPDK or RDMA. And in many cases, Axio also outperforms traditional sockets in CPU utilization. And in summary, we presented Axio, which is a system that preserves familiar POSIX abstractions for us and also achieves kernel bypass performance. Our proposal, Axio, modifies the CPU microarchitecture and provides a hardware-software co-design for I/O, inspired by virtual memory and TLB. We introduce an I/O connection table and an I/O ready queue to enable fast process wake-ups. We also use hardware-assisted scheduling and optimize interrupt delivery systems to improve the performance and let us match the kernel bypass systems. And finally, using an FPGA prototype, we showed that Axio can achieve low latency, high throughput, and reduced CPU utilization. Thank you for your attention, and feel free to reach out using the contact shown in this page. Thanks.
Fantastic stuff. So any discussions from the audience?
Hello, everyone. I'm Tanya Sridhar. I'm a postdoctoral researcher at UD.
Any discussions from the audience?
I really like this. I never thought about time change. CPU environments that were network.
I agree. I also wonder what the future is for these approaches that try to balance performance with elegant and simple to use abstractions, because I suspect in the coming years, we're going to increasingly automate the production of this type of code. So what we might find is that simplified abstractions are no longer necessary because we're using models to generate all of the code anyway.
I'm just curious, because in the motivation they are using several of the MPS yeah. How do they work? Do you have any? Probably
Yeah.
I get like 80 times inside.
Yeah, but it sounds like we have quite a lot of interest in the audience, and some of these questions perhaps are perfect for offline discussions with the authors, who I'm sure are really keen to receive emails from everybody. Any other discussions from the people at the back? In which case, in this session, we've got just time for one more presentation. And a quick reminder, I think the microphones are a little insensitive to our voices. So when you speak, if you speak loudly, I think the people on the Zoom screen would also be able to hear better.
Oh, I think we can try to do this. Yeah. Remember in the morning we try this map, but it doesn't move. This one. We can only do this one. But even for this one,
Not very much.
it's not straight up. It should be the green line going up and down.
1, 2, 3.
Great.
Let's try this other one. Okay, so let's move on to our next presentation, No Signals to Rule, and let's hit the play note.
Hi, my name is Sarah McClure, and today I'll be talking about our paper, No Signal to Rule Them All, a systematic analysis of in-network congestion signals. Suppose you're a congestion control algorithm designer, and you've been asked to design a new CCA. A reasonable first question you might start with is which signals to use to detect congestion. You might use delay, ECN, or one of the many other possibilities. To answer this, you might look to previous work and see many different answers, all with different objectives, assumptions, and more. To make matters even more complicated, while you're considering each of these signals, a switch designer comes to you and asks which INT, or in-network telemetry, signals they should provide. These signals are collected in the switch and appended to packets, and therefore can expose fine-grained information about congestion, such as the queue lengths, to the host for your congestion control algorithm. So now you consider even more work that explores different INT signals. With all this information, you begin to contemplate various questions like, which is the best signal of the available options? If you could use a particular signal better than the existing algorithms do? How your goals are different, how your network's different, and more. And in the meantime, the switch designer has to follow hardware design cycles. Thus, we sought to ask, what INT signals would be most valuable for CCAs? Here, let's first consider a naive approach to answering this question. In this approach, we could start with some modern CCA. Here, let's take Swift as an example, which at a very high level uses precise delay measurements to detect congestion. We could create two variants of it, one that uses the link utilization INT signal, so the sender receives the max link utilization seen along a given packet's path, and another that uses a queue signal that reports the max queue length along the path. We could then evaluate and compare the performance of each of these algorithms. Let's assume, for the sake of this example, that the queue version does better than the baseline, which does better than the link-based version. Accordingly, we could decide that queue signals are better than delay, and delay is better than link signals. But this approach has several issues. To name a few, what if Swift's control loop is just not designed in a way that using link signals makes sense or is effective? What if you could improve baseline Swift for even better performance? Would the ordering change? What if you're using a different algorithm than Swift, either now or in the future? Will these findings still apply? And what if your goal is different than what Swift was designed for? Thus, with all of these open questions and more, we return to our question, but now with a methodological challenge. How do we answer this in the general case? And by that, I mean over many possible networks, objectives, and for all possible uses of the CCA signals, meaning how the control loops of the CCAs react to a particular signal. Thus, we took the following high-level approach. Suppose we had the optimal CCA for a given scenario and signal. We could compare these optimal CCAs and thus determine which signal is best, since the best possible CCA that uses that given signal is better than all the best CCAs for other signals. More concretely, we could choose our network setting, which defines things like the link rate, latency, etc., and a goal metric, here per flow utilities, and describe a particular set of signals which the CCA can use. We can then create the optimal CCAs for each set of signals that we want to compare. Here we have two different signal sets, S1 and S2. And then we can evaluate these CCAs and compare their overall performance. If CCA1 does better than CCA2, we can decide that the signal set 1 is more valuable than signal set 2. Now, of course, we don't just have the optimal CCA for a given setting and signal set. Thus, we approximate this with learned CCAs, where instead of generating the optimal CCA, we take the best performing learned CCA for the given scenario. Importantly, one of the main pitfalls of learned CCAs does not matter here. We do not need these CCAs to generalize to anything outside of their training set of network scenarios. We want the best CCA for a particular setting. To make this more concrete, we took each parameter and gave this to our CCA generator, R+. R+ is our improvement over a seminal piece of work in the space of automatically generating CCAs, REMI. We found that R+ produces better performing CCAs than REMI and better than performing parameter tuning of existing CCAs. Notably, we tried other learned CCAs from prior work and found them to perform worse. See the paper for more details. We then take the learned CCAs and evaluate their score more thoroughly in NS3, producing a final score. We then repeat this process for multiple signal sets, compare the final scores, and thus determine the signal sets that are best. I'll give a quick overview of our findings before diving into more detail for some of them. First, we found the surprising, at least to us, result that with these optimized control loops, in the average case, INT signals did not offer much over end-to-end signals. In more detail, we found that only very coarse end-to-end signals consistently performed worse, but that INT could provide performance improvement in some extreme cases, and in all cases, it was better at achieving multiple goals at once. Secondly, we found that there's no clear best INT signal of those that we tried. Each one has its own strengths and situations where it performs well. In this talk, I'll focus on a few of these findings, but see the paper for more details on these and other results. Before diving in, let's define our configurations. We chose two network configs that both defined a space of networks with ranges of RTTs, bandwidths, etc. We evaluated on a family of utility functions that generally weigh throughput against per packet delay and varied the weights to emphasize different goals. As an overview, our default utility function equally weighed throughput and delay. We also have a version called 2T, which weighs throughput twice as much as delay, and a similar one that weighs delay twice as much as throughput. And we had two very extreme versions with weights of 101. Lastly, we considered four main signal sets. End-to-end signals, which includes RTT, the sending rate, and the receiving rate, all of which can be measured at the host. Link, which includes the end-to-end signal set and a link utilization INT metric. Similarly, we have Q, which has the end-to-end signals and a Q INT metric. And lastly, link plus Q, which has all of the above signals. Of course, changes to these parameters may produce different results, but we believe our parameters are a reasonable and representative starting point. First, we'll show the average score or utility across different signal sets and utility functions that weigh throughput and delay equally or prioritizing one of them twice as much as the other. As you can see in the plot, none of these are significantly different. Even with utilities that care more about throughput or delay, all of the signal sets perform within error. But notably, these results are averaged across a large set of network scenarios within the network config. So what about specific scenarios? Here, we plot the difference in score between the link and queue CCAs and the end-to-end CCAs, specifically the full distribution across all evaluated network scenarios. Even with very extreme utility weights, the differences are small, at most up to 10%. Though notably, they can sometimes be significant. For example, we found a significant score difference in about 11% of scenarios under equally weighted or default utility. And in general, we found that these differences were at the extremes of the network config. So for example, in cases with the highest load. Despite the similar scores, we found that INT was consistently better at the metric that was not prioritized by the utility function. Here, we'll refer to the higher weighted part of the utility as the primary metric, and the secondary is the lower weighted part. Thus, the INT signals were better at the secondary metric. Here, we plot the percent of cases where INT performed significantly better than the end-to-end signal set in the primary and the secondary metrics. For example, with a utility function that weighs throughput twice as much as delay, link achieved better delay, which is the secondary metric, than end-to-end in every case, while end-to-end achieved roughly the same throughput as the link version in every case. And this pattern is true across all utilities and signals. That INT and end-to-end achieve about the same in the primary metric, but INT can potentially do much better in the secondary. But because the secondary metric matters less to the overall score, it doesn't affect the overall difference much. Lastly, we found that each INT signal has different strengths. First, we investigate how each signal does better or worse. Here, we show the percent of cases that link or queue achieved better performance than the other in either delay or throughput. When compared against one another, link signals often had better delay than the queue-based INT, while the queue often had a slight edge in the throughput. We found that link achieved its low delay by staying near but below 100% utilization, while the queue metric would build a small queue that would maintain some queuing delay but ensure high throughput. Now we consider when each signal did better than the other. And we found that these strategies led link metrics to help in higher load situations to avoid queuing, while queue metrics helped in low load to ensure that ensure throughput by always filling the pipe. While I don't have time to get into this in detail in this talk, we found that these results were robust to multiple hop topologies, multiple bottlenecks, and different variants of the signals. One notable scenario, though, is reverse path congestion. Here, we assume we have some forward path traffic, but its acts are getting delayed by many flows on the reverse path. Ideally, the forward flow should not back off simply because its acts are delayed. And we found that INT signals did help in this case, both in many particular scenarios and on average. However, we also found that a one-way RTT could do the same or better. As you can see in this plot, all INT signals do a bit better than the end-to-end, even on the average. And we found that there is a significant score difference in up to 60% of the evaluated cases, which is much higher than the 11% from before. But a one-way delay, here in pink, does just as well, and in fact, a bit better. While an accurate one-way delay measurement is a big practical challenge, this result indicates that properties like the domain over which the signal is measured can be more important than the metric itself. Lastly, we applied our learnings to two existing CCAs, BBR and DC-TCP. In BBR, we added INT signals to the existing logic and found that while we could improve the performance, we could also get the same gains with RTT. In DC-TCP, we made versions of it using RTT and INT signals instead of ECN, and all performed similarly. Thus, our basic result holds even in real CCAs. In summary, in this work, we proposed a methodology for determining the best INT signals, and found that while INT signals have their strengths, they do not perform that much better than an optimized end-to-end control loop. As I mentioned earlier, all of the results I presented are for a particular space of networks, utility functions, and signals. While we suspect the results will hold beyond these values, we hope that future work can determine the generality of these results. Our code is available for more extensive evaluation and extensions to the setup and configuration space. We look forward to future work in this space. Please reach out with any questions. Thank you.
Great stuff. Okay. Audience, do we have any thoughts or discussion points?
I just really remind me of Keith's work.
Yeah.
So I hope they could. So I know he stopped supporting that or working on that, but then probably we could talk to him and see how we can actually sort of try this out on anything. Just that's a real like
So
real kind of playground.
it looked a little bit like R Plus was built upon Remy, so I guess maybe there's some interaction between them and Keith already.
Yeah, so it's quite interesting. It's kind of a bit like new, like or like the beacon of interest in looking at conversion for more systematic. And it's I mean in general I quite like this because now there's also like two protocols, quick fix systems, and so we also have more options to provide better systems. And so it's nice. So the other paper that we had this contracts paper, I happen to know this work is also quite interesting. It's about like formalizing like promises or that production make. And it's interesting to see that after all these years, people are still finding new perspectives to look at it.
I mean, I guess, I guess in a sense, the complexity that was presented in the talk gives the reason for why the research continues, because there seems to be no one solution that fits all different scenarios.
Yeah, also we have like maybe also new workloads, like say AI training or inference that have slightly different requirements. So it's also worthwhile looking at this and designing like these full protocols that support just these workloads really well.
So let's say if there's no signal that can connect out by information. How will the hardware manufacturer design your operating systems? Did you support all the signals? And the algorithms enable by their own experience?
Right, that's the question. Right? So I mean, of course, right now this is very experimental still, and we can see what values, so signals and maybe. But I mean, you can do many things with one of the hardware. Right? You need to implement this to
Great. So for the benefits of the remote audience, there's a lot of discussion taking place over here, a lot of interest in the paper. But at this point, I think we're going to transition over to our keynote speaker. So it's my great pleasure to invite to the stage Hong Xu, joining us from CUHK. He's undoubtedly one of the main SIGCOMM players in the Hong Kong region, and today he's been kind enough to join us for a keynote. So with that, I'll hand over and switch to Hong. I've sent you the link to the Zoom, so you just join through that.
I can also tell you the meeting ID, so
He's got
stop sharing here.
So just a quick reminder to the room as well, the microphone is situated here at the podium, so if you ask a question, shout.
So just share screen.
Right.
So you can either join the projector here, or you can also share from this to whichever.
I think it's easier to just let's, because that's working. So I just vote not to change that. If we share the screen.
Okay. That's fine.
I can check. Yeah, it's sharing perfectly.
I think you stop sharing, so you need to share this page.
Nope. Okay. Switch it up. So good.
Yeah, it's only this.
Okay.
Great. Okay, with that, let's hand over to our keynote speaker.
Thank you. So I'm really happy to be here for the first
NINES experience at UST. So I'm going to talk about hyperscale AI infrastructure. So I will try to cover both efficiency and also reliability. And so before we start, I just want to give you a little bit of background, but I think it's pretty well known. So infrastructure is really important for all the AI workloads, large language models, and perhaps we don't need to see a lot of evidence about that. But just a little bit of like anecdotes. So the kind of the scale of, for example, number of GPUs that these big players in the AI business are using these days is crazy, right? And this is just last year, and right now it's probably even larger. So there's a lot of interest, there's a lot of investment in this space, and perhaps the most direct sort of evidence about this is that is if you take a look at the stock price of these NVIDIA, for example, right? It's been going up crazy. And compare that to, for example, some other players like Apple that are not really that big in the AI space, so you can see a clear difference. All right. So what I'm trying to do in this AI infrastructure and also systems kind of the space here is basically these four major topics. So first of all, obviously, we want to look at performance. We want to accelerate training and also inference, and we want to do that at scale. So we've looked at a bunch of really interesting but different kind of models and workloads. So today I'll be talking about the DIP models, and we've looked at, for example, MOE a couple of years ago, and so on and so forth. And the second part is about the so-called compound and complex ML workflows. So this means that in your workflow, so think about basically agents, and like if you go back a little bit, RAG and stuff. So you no longer have just the models, the LLMs that are working here. You also need to involve external tools and perhaps a bunch of models that are working on different like sub-problems of your task, and then you need to illustrate them. And you need to think about performance. You need to think about, for example, how to share more efficiently share the KV cache, the context across these different models, and so on and so forth, right? So this is also something that I think is there's a lot of opportunities in here. So that's the second thing. And the third theme is trying to make things reliable. So basically reliability engineering. So we've looked at like sort of two things. One is how do you provide better tools, tracing tools, monitoring tools to support the AI workloads, so that whenever there is a failure, it's probably a lot easier for you to find out the problem and where that is. And the second is RCA, root cause analysis. So we want to develop basically agents that can autonomously troubleshoot and diagnose and mitigate problems whenever they occur. And so this is going to be especially useful when you are running really hyperscale infrastructures and you don't want to really deal with problems that comes up when you are training over, let's say, 100,000 GPUs. And finally, we are also working on simulation, both for training and also inference. This is kind of maybe slightly like a niche topic, but actually recently I've seen a lot of new papers that are also working on this. So apparently to the industry, this is actually very fundamental because before you do all those innovations, you want to really sort of try out and understand the trade-off between these different decisions. And so before you commit, if there are some simulation tools that can help you do that, make those decisions, then it's going to be really helpful. So that's basically everything that we're working on right now in the space of AI infra. So essentially, there are two major themes. One is performance and efficiency, obviously. The other is reliability, usability, and beyond. Right? All right. So I've also been working on networking for a very long time. So we're still working on that. So we are looking at cloud and also data center networking for a long time. So we've been looking at the data plane and also management plane. We've also looked at like virtualized network stacks in the cloud and so on and so forth. Okay, so that's kind of a quick overview of my research. And so today I'll be talking about mostly two things, right? So the first project is about large-scale video DIT training. So this is about performance. And essentially what we want to do here is to look at and also to exploit the dynamic sparsity patterns that are inherent in these models. So this is going to appear in ASCLOS next month. All right, so here we're looking at a very, very interesting and really promising application for large language models, which is text-to-video generation. Okay? So basically, I don't know if you guys know about this, but basically, all these T2V models are based on diffusion framework. And so this is sort of the backbone. And essentially, we are still relying on the plain old, transformer kind of architecture to build the model. And specifically, we are still relying on full attention, okay, to model all these relationships across different tokens of the videos. And this is basically just to guarantee that we have the best quality videos generated to use. Right? So if we take a look at this example, which is from a model coming out of a startup startup called Step from early last year. Okay, so basically the prompt is that we want to generate a video with a Chinese girl dressed in a traditional outfit and smiling, and holding a piece of paper that shows we will open source. And here's the result. Right? So this is a short video, but nowadays, because this was like a year ago, but nowadays, if you look at the really recent models, T2V models, they can generate videos up to a few minutes long that are very consistent, across this whole timeline. But yeah, so this has been advancing a lot. And so we want to look at video DIT and particularly training in video DIT models. And so the problem here in training these models is that you just have a really, really long context with a huge number of tokens that you have to process with full attention, right? So even when we are using latent, we're working on this latent space. If you just look at the number of frames that you're going to have. For example, if your video is 30 frames per second times how long the video is going to be, times the dimensions of the latent space, then you can easily get over hundreds of thousands of tokens. And you have to run full attention across all of these tokens. So you have to start from exactly frame 0, and then compute all the way to the last frame, right? So easily full attention becomes the bottleneck across this entire training pipeline because of the n-square complexity. And you can see from the figure at the bottom. So we did some experiments to train DIT models of different sizes, and then we take a look at the portion of time occupied by the self-attention calculation. And so you can see that as the token length grows over 100K, then already the attention computation completely dominates the whole time game, over 90%. So that's the problem that we want to address, and this has been observed for a very long time, and so people have tried to look at that from different angles. So in terms of training, people have been trying to use different attention mechanisms. For example, hybrid full attention, spatial temporal attention, and even sliding window based attention, which is heavily used in text models. But you can also apply them here, right? So you can easily reduce the input size and therefore the number of tokens you need to process. And there also has been a lot of recent work about how to accelerate inference of DIT. So our approach here is that, well, before we start to do anything, we decide that we want to actually take a very close and very deep look at the attention scores in DIT models first. Because if we look at existing approaches like sliding window attention, those are mostly developed for text-based models. But videos are supposedly very different. So we really want to understand the workflow first before we do anything. And we did find something that are really interesting, which is actually the things that I really want to share with you guys today. So what we did is that we trained a reasonable size model, 2.7B, similar to MovieGen, and then we trained that over 8 H100 GPUs with the open data set. And we performed training from scratch, and we observe the attention scores, what kind of patterns do they have, and then we'll make a number of interesting observations here. So first of all, we do see that the attention scores, they have a very clear power law distribution, which you can easily see from the figures here. So this just means that a very small number of the key value pairs, they would contribute to most of the attention scores, which essentially means that these are the most relevant or important key value pairs that we should look at, right? And so this is consistent with all the prior work, again, for text LLMs. So that's not surprising. But then the other observation, the second observation that we see for video DRT is that if we look at the locality patterns of these so-called critical KV pairs, which are essentially, the ones that control to the majority of the attention scores. If we just look at these critical KV pairs, we do not see any locality patterns, which is actually completely different from text LLMs. So for text LLMs, there's a locality pattern because what matters to this particular word is probably the most, the immediate words or sentences that precedes this phrase, this word. But that's not the case in videos, right? So you can see the plot on the right where we show the green dot. So the green dot is the query that we want to look at, and then all those dark dots are basically all the critical key value pairs associated with this green dot. And we plot that for 4 different attention layers or attention blocks, and then you can see that basically, depending on which layer you're talking about, it could be everywhere. There's no parity, right? So that's that. So this basically means that we probably cannot apply approaches like sliding window because you don't have that locality. It doesn't make sense for you to just look at a few previous tokens before this particular token, right? So the other observations we make here are basically spatial and also temporal diversities regarding the attention scores. So from the figure on the left, you can see that there's a very clear spatial diversity across all of the attention layers when you look at their sparsity levels. And also, even if you just look at one particular attention block, different heads within that attention block also have very different sparsity levels, less relevant things. And so there's no not much sparsity, but gradually you learn to focus on the really important features, and then that's where the sparsity naturally comes out, right? So that makes a lot of sense here, essentially. And the last observation is this. Basically, so what we see is that although there's a lot of diversity across different heads and so on, but when we look at tokens that are very close to each other, adjacent tokens, and we do see that they tend to share a lot of similar critical key value pairs. So you can easily see that from this figure. But I want to convince you with just a simple example here, which is a picture of a badminton game, right, between Ling Dan and Li Chongwei. So what I want to highlight here is that if you look at where the shuttlecock is, which is basically there, right, and you look at the 2 players, for example, you look at different parts of this player, they naturally need to attend to where that shuttlecock is. And so this essentially is saying, all these adjacent tokens, right? They tend to focus on similar, or they share similar critical key value pairs essentially. And it's the same for the other player, and it's the same for a lot of the photographers in the background, as you can easily see. And this sort of also, this example also tells us the other observation that we made in the previously, which is that although they're looking at kind of the same feature over there, but you can see that they're not necessarily looking at things that are close to them, right? So the shuttlecock is closer to lean down to the player in red, but it's quite far away from the other player. But that's okay. They can attend to objects that are very far away from themselves, actually. All right. So all these are the interesting observations that we make from video DIT models, and naturally we want to develop a system that exploit all these features to accelerate training. So essentially we want to utilize this dynamic sparsity features for videos, right? So we want to just use the critical key value pairs instead of all of the key value pairs in the attention calculation, so we can save time in both compute and also communication. So this sounds great, but obviously there are a lot of challenges in here. There are three essential challenges. One is that if we want to use those critical key value pairs, how can we find them? It's actually not that straightforward, because in order to identify critical key value pairs, we have to compute the softmax QKT. But if we do that, then actually we are already getting all of the attention scores, and essentially we're already doing the attention calculation. So we don't want to actually just calculate this attention score, but we still want to identify these key value pairs. So that's the challenge. The other aspect of this challenge is that if we naively just calculate these QKT, then we would actually break those fused kernel implementations like flash attention that everybody is using these days, right? So flash attention fuses this QKT calculation with the other components in the attention, so that it becomes highly efficient. But if we just want the softmax part, then we will have to break it. It's going to be quite slow, actually. So that's challenge number one. We want to really efficiently identify, and we want to do that dynamically because all the sparsity patterns actually changes over time. So challenge number two is that suppose we are able to dynamically find these critical key value pairs, how can we actually sort them, right? And how can we actually run the attention calculation? Now, this was sparse attention calculation. So the problem here is that if we naively sort all of the scores, using top K, then there's a lot of memory overhead, and also it breaks the. If we do the attention calculation just over these critical key value pairs, then we have very irregular memory access patterns, which again diminishes the utilization of the tensor cores, and then the efficiency is very bad, right? So this actually is a pretty big challenge for us. Later I'll show you why this is the case. And three is actually communication. Okay, so in order to also handle this long context training problem in video DIT, people have been using things like context parallelism, which basically means that if I have a very long sequence, then I can sort of divide up the sequence into different chunks and then assign them to different GPUs. So in order to balance the workload. And so the problem here is that now since we're using sparsity, so now for example, different GPUs might be seeing different amount of workloads and different amount of data that they need to transfer across the network. So it becomes a heterogeneous situation instead of homogeneous, like what people have been assuming before. So we have to rethink about this in the context of sparsity. So essentially, we built DSV, this new system to tackle all the three challenges that I just talked about. So it works on three things. One is algorithm, which basically is for challenge number one. And then we developed efficient kernels for challenge number two. And three, we also worked on context parallelism, and we optimized So we have sparsity aware context parallelism that can rebalance these workloads across the GPUs. So I'll very quickly go over the basic ideas here. So for critical key value pair identification, so essentially our idea is to apply low rank approximation, which has been used also before in a lot of the ML papers, right? So what we do is that, well, if we look at the figure here, which is the first stage of our training process. So what we do here is essentially we profile, okay, the sparsity levels of different heads across different attention layers, and then we use that to also train two low rank matrices for each head, okay, of each block, so that the product Q, so the product of these low rank matrices approximates the original QKT. And we do this low rank training actually independent of the regular training. So in the sense that the regular training is still done with very efficient kernels like flash attention. But occasionally we will sample we'll sample the data points, and then we will train these low rank matrices. So this becomes the first stage. And once we finish the first stage where these low rank matrices gives us very good approximations, then we switch to stage 2, where we simply just apply these low rank approximations to tell us, to sort of predict intention scores of QKT, and therefore we can apply the kernels later on to see whether we should use the sparsity or not, and what are the critical key value pairs and the indexes of these critical key value pairs. All right, so that essentially is this part over here. So once we're able to find, the critical key value pairs using low rank matrices, then we need to we need to actually apply those attention calculations through these kernels. So what we did here are two new kernels. So one is a fused Metmol with top K kernel, so that we can estimate the critical KVs with very low overhead. So essentially, the insight here is that you don't need to really run top K. You don't really need to materialize the matrix multiplication result, because all we need is to keep the top K results, so we can fuse them together into an intermediary calculation. We just need to keep the top K results. So that's that. And then the second kernel we developed is the sparse attention kernel. So remember, the problem here is that once you have sparsity, then you could be just you need to just calculate those small number of pairs, but they're everywhere. They're not contiguous in memory. So that really breaks your memory efficiency over here. So what we want to do is to utilize our last observation, where we see that adjacent queries actually do share a lot of critical key value pairs. So we decide to not just calculate this sparse attention for one or a few queries, but rather we calculate this for a group of queries that are adjacent to each other as a block, and then pass that as to the kernel, as a way to maximize the memory efficiency. Right. So if you look at the comparison here, for example, this is how much time it would take for the regular for attention with flash attention, and this would be what you have if you just naively use top K and then you just naively apply your sparse attention without query grouping. And the third bar basically shows the actual optimized result after these efficient kernels. And so only with these kernels you can actually materialize the gains that seems to be pretty easy to achieve, but actually if you have the wrong implementation, it's actually going to be quite worse than the full attention. Right. So the last thing we did is sparsity aware context parallelism. So essentially, like I said before, when you do context parallelism, you either divide up your long sequence across different GPUs, or you keep your long sequence but then you divide up your attention layer, so different GPUs just hold a small number of different heads within that attention layer. So either way, they will have imbalanced workloads or redundant transmissions with sparse attention here. So what we did here is to basically use hybrid pet-wise and sequence-wise context parallel. So we want to find out basically the best configuration given for each attention layer, given that they have all the heads and all the different attention layers at different sparsity levels. And so the approach that we use is essentially to try to model the kind of workload that each GPU is going to experience given a specific context parallel setup. And we try to model this as an optimization where the objective is simply to minimize the maximum sort of time that it takes across all of the GPUs to finish the transmission. All right, so that's the essential idea over here, which is quite straightforward. Okay. Anyways, so we did implementation of this DSV over PyTorch FSDP, and so it's all open source. The repository is over there, and then we use quite a bit of GPUs to run training of based on DSV, and then try to compare them against the baselines like full attention and also sliding window based attention, WA. And so here are some of the results that I want to show you. So first of all, obviously, we want to convince you that even though we're just using the critical theory of pairs with sparsity, but we don't really lose out in terms of performance. This is the really important part. And so if we look at both training and also validation loss figures, you can see that compared to, for example, window-based attention, WA, in some cases, like on the figure on the top left, you can see that window-based attention actually doesn't really converge. The training doesn't really converge with that. But with DSV, training always converges and loss curves stay very close to the full attention curve. Right. And we also look at, so we basically follow all the prior work, and we look at different kind of quality metrics to assess the video qualities generated by different approaches. And we do that over different data sets. And essentially, the observation is that DSV is able to give you very consistent quality compared to full attention, but much better than window-based attention, which obviously don't work well in mediums. And we even did a very small scale user study. So we asked a bunch of people to actually look at the video clips generated by these different approaches and then give us a score. And so that basically tells you the same conclusion, right? So with performance, then we want to look at actually how much efficiency or efficiency gain we can achieve with DSV. So we first look at training throughput, which is essentially what DSV is for. And so across different settings and also different models with different sizes, then you can see that we provide up to 3 times speed up over full attention, and also provide up to 1.5 times gain over window-based approach, right? And I want to mention here that we could also apply most of these ideas over inference, although we're developing this for training. But you could also apply this over inference, where there's no context parallelism, but all the other things like efficient kernels would still apply, and you can still get pretty good performance gains out of there. Okay, so that's the first project that I want to share with you. And so that was about performance. And so in the second part, I want to talk a little bit about reliability. And so I want to introduce Mycroft, which basically is a tracing tool that we developed with ByteDance that help people to find and identify root causes of anomalies during LLM training. Right. So we want to look at these essentially these 2 types of anomalies in training. One is called grade failures, the other is stragglers. So grade failure, essentially, they are failures in the sense that they would stop the training job from making any progress. So they're pretty severe, but then the thing about them is that they don't really give you any sort of immediate alerts. So you have to observe these grade failures as after a little while, and this really becomes a problem because before you can catch these grade failures, a lot of your hardware components like GPUs are idle, and once you have these grade failures identified, what you can do is to restart a job from the most recent checkpoint, which is going to take actually a lot of time as well. It's going to take like anywhere between 30 minutes to 1 hour for a reasonably large training job. And stragglers basically just slow down the training, but they don't completely stop the training. So sometimes they're caused by long-term, bottlenecks, but sometimes it's just fluctuations or hiccups. But anyhow, we want to be able to find them, and we want to be able to do something about that, right? So the problems with handling these anomalies nowadays is essentially twofold. One is that in practice, they're often detected way too late. Okay, we can't really catch them as soon as they occur. And second, when we are able to actually detect these problems, it's actually really hard for us to locate or pinpoint which one is actually the culprit here, which one is the sort of the originating hardware or software components that gives us the problem. All we see when we detect the problem is that the whole job fails and a lot of nodes are affected, but that's not enough information, right? So I'll give you a real world example. So this was from ByteDance's production experience. So what you have essentially is just a single defective GPU that stops working. But as soon as that happens, it causes simultaneous communication stuck across all of the ranks. First of all, within the BP group, and then very soon across all of the jobs. And pretty soon you can see that there's zero network traffic across all of these guys. But that itself doesn't really manifest as any sort of failure. So your monitoring systems wouldn't immediately give you any alert saying that, okay, for 1 second, there's no traffic across this network. Maybe something, is there something that you want to look at? Probably not, right? And so at the end, this job actually failed after 10 minutes by triggering a nickel timeout. And that's when the user was notified. And that's when the infrastructure guys are notified that there's something wrong here and they come in. But this is already very late. And the second problem, like I just said before, is that once you know there's a nickel timeout problem, you have no idea what is going on. So what the engineers have to do is to, for example, run offline benchmarking tools and even to rerun some small-scale model training across maybe part of these GPUs, just to really localize where is this faulty GPU, where is that problem, right? So all this is really problematic for us. And the root cause of the problem here is essentially that we don't have enough visibility or observability, especially into the collective communications. Because when you think about it, the problem propagates because there's a lot of collective communications. If we can somehow get into the progress of these collective communication operations, we would be able to better trace how this anomaly propagates, and therefore we would have much more information to tell, like who starts to experience problems at first, and therefore the root cause is probably over there, right? So the idea is actually very straightforward. And when we look at all the existing tools and systems that we have, they actually don't give us that kind of capability. So if we look at tools that look at different operations, OP level tracing tools, they don't have any fine-grained information into the progress of of each collective communication, and they don't really utilize like all the dependency informations that's inherent in there, right? And they don't give us any like real-time anomaly detection or root cause analysis kind of capability. And so there are also kernel tools like Insight, but again, they don't give us fine granularity into what each collective communication is actually doing. What they give us, as I will show in a minute, is basically just a bunch of timestamps, but that's with regard to the whole operation or to the whole kernel. Okay, so it doesn't give you any information about what's happening in the middle of that operation. So what we really want to essentially achieve is that there's a tool so that it looks at, it traces the collective communication or the co-OP or the kernel. And when that OP is somehow stuck, then we want to know that right away. And then we want to know exactly which OP and where, whether it's RDMA or whether it's the GPU, where did that happen? Okay, so that's what we want to build. So to just give you another example of why existing tracing tools doesn't have that capability. So if we look at the figure on the left, so this is an example with Insight. So we've turned on Insight, it traces all these different nickel operations. But what it does essentially is to record the start and end timestamps for each of these kernels when they finish. But what if they don't finish? What if something happens in the middle of that? So after we inject a failure, represented by this red line over there, then you see that you don't get any kind of traces from all of these GPUs, from all of these ranks. But we only inject a failure into one of the ranks, right? But because they're all dependent, so none of these collective communication OPs can make progress, none of them can finish, therefore it's not possible for Insight to give you the end timestamp, and basically it doesn't return, right? So you don't get any information, and so that's not useful for us in this case to know what's really going on. Right. So we want to basically have fine-grained core-level tracing, so we know exactly what is going on, even when the OP is stuck. And so we decided to do this fine-grained tracing on two levels. One is at the flow level, which essentially is the network flows granularity. So we want to be able to see like what's going on between for each of the nickel channels, which is essentially what we was trying to do to transfer data in parallel, right? And we also want to have trunk level information because trunk is the smallest unit in nickel to transmit data. And we want to be able to see what is happening at the trunk level, but we can't really just ask we can't really just trace what's happening to each one of these single trunks because that's going to generate too much data and also too much overhead. So what we did is basically to aggregate these trunk execution data periodically, but we do that at a few critical hardware and software components, for example, GPU, and then RDMA, and some memory copying like points over there. Okay, so this way, for example, we can quantify the amount of data that has been transmitted so far during a OP in different flows, in different channels, and this way we can get more visibility into the progress of each OP here. Right, so so that's basically the whole idea behind Mycroft. So we built Mycroft as a collective level tracing system. This is the overview of the system. So we built this into the Nickel CPU proxy process. And so it basically writes all the tracing data into a shared memory and it pushes that to centralize the DB. And once we have these data, then we will try to monitor these data in real time and then give us anomaly triggers once we detect something suspicious. And so that will eventually go to a dependency aware root cause analyzer that will try to look at the problem or the traces and try to find where exactly is the root cause here. Right? So it It is mostly tracing too, but it also has anomaly detection and RCA capabilities. Although it's kind of the RCA capability is more based on heuristics capability. Right. So finally, if we are not able to detect the actual root causes, then we can give all the information to the users, and the users will be able to perhaps do more investigation. All right. So I'll just very quickly talk about the design, design of this system. So for the tracing instrumentation, basically we have two types of trace points. So as you can see here, one is completion log, which basically is quite similar to what Insight is able to provide to us. So they can log both the start and end timestamps of each OP or each kernel, along with some other meta information, right? So this is only generated when an OP is finished. And second, Mycroft is able to give us real-time state logs so that we can really track the progress of each OPM kernel. So this is really essential for Mycroft. So we do this periodically every 100 milliseconds, actually. And we do that even when this OP is stuck, is not finished. And then we collect all of these information in terms of metadata and also in terms of like trunk level execution progress. For example, what is the time that it's been stuck, total number of data transmitted on this trunk, and different status at different critical points of the transmission. All right, so then with these tracing information, we can do dependency-based RCA. So I'll very briefly talk about this because it's all heuristic. And actually, you can do a lot more here to improve the RCA capabilities, which is also something that we're trying to do right now. So essentially, the logic here is that we wanted to do two-step kind of approach to detect the root cause. One is that we want to locate the anomaly, basically which rank is the anomaly here, right? So we do this in a dependency-based fashion in the sense that we can identify, for example, the straggler is essentially the first flow that always takes longer to finish compared to the rest, or it just always starts a bit later compared to the other sources. So quite straightforward. And so once we have that abnormal rank, we could execute perhaps step 2, which is try to do intranode RCA to really identify whether, for example, the problem is on the GPU side or on the RDMA side or some other things maybe on the network, right? It's not on the NIC. And so remember in the real-time logs, we do have these information about different critical points and the progress at different critical points. So based on these rules, then we can very confidently kind of determine what is actually the root cause here, whether it's GPU problem or not, right? So that's the essential logic. And if we go back to the same example that I showed you before with Insight, once we inject the failure to one rank, and then all the ranks, you don't see any traces from all of these ranks. But with Mycroft, then you don't see any traces from the faulty sort of ranks, but you do see completion logs, the red dots still coming out from the rest of the guys here. So that clearly tells you that there's some problem with people that don't give you anything at that point, right? And so that's essentially why this is quite useful. All right, so now we've deployed Mycroft at ByteDance's production cluster since actually October 2024, and so this has been running since then, and this has been used and integrated with some other debugging tools that they've been using. And there are a lot of the results, but I have to skip most of them, but just to give you quite a few of these. So first of all, I want to show you sort of the CDF of both the trigger time for detecting anomalies and also the RCA time, the root cause analysis time. So we were only able to collect 2 months of data before we submit the paper to SOSC. So during that time, we were able to catch all of the anomalies based on cross-referencing with all the other tracing and monitoring tools after the fact. And among them, we perform over 1,200 root cause analysis. And so basically, 90% of these cases, these anomalies were detected within 15 seconds of onset, and 60% of the analysis were able to complete that within just 20 seconds. Right, so that's a lot better than seeing a nickel arrow 10 minutes after the fact and spending hours to debug. The system has very low overhead. So if you look at this figure on the left, compared to the baseline, Markov basically only adds a couple of milliseconds overhead to the step time. Whereas if you look at the very right, the bar on the very right, where we turn on NSAT with backtrace, then actually that overhead is extremely high. It goes over, in some cases, goes over 2,000 milliseconds for each training step. Right, so this is very important for production. And I'm not sure if I have time, but maybe I'll very briefly talk about this case study. So here, essentially, it's a real case study where we experience a problem with a straggler, okay, within a 128 rank DP group, and so we immediately see the problem because it's very easy to see there's a straggler from the traces, and then we want to do intranode RCA in here, and essentially what we're able to see is this figure. So we look at these 4 different nickel channels for this particular OP, that's actually an all-gather OP. And then we see that it actually is channel 0 that starts to experience some problems first. So initially it was transmitting, but somehow it got stuck. There's no data for quite a long time, and then it starts to go again. Compared to the other GPUs, they don't have this stuck period of time in the middle. So because it's channel 0, so we were able to actually also pinpoint that the problem is related to the GPU instead of the network or the NIC, because all the other channels are okay. They don't see that problem, and so with that information, we can actually determine that actually the root cause was this one SM that's associated with this channel 0, okay, on this root cause GPU. That has some problems and causes that is stuck. There's no data basically generated because of that reason. Okay. All right. So I want to quickly just share with you some of my thoughts regarding what can be done in the future in terms of this AI infrastructure and AI systems. So I do think there's a lot of really interesting things here. So one, which is very related to us, networking people, is this scale up networking, right? So there has been a lot of new basically hardware, right? That, for example, this cloud matrix thing from Huawei and the UV from Huawei. So basically now you have a single interconnect that connects not just all the GPUs on one machine, but across machines, and even sort of unify all the memories as a single pool within that pod. So it will be very interesting to sort of rethink how the software systems will have to be designed, in the sense that now you don't really have just 8 GPUs within a server. You have 384 GPUs within a node, and so that's really some opportunities there. And the other is RL infra. So RL is getting lots of attention just over this last year, because RL is a very interesting workload. It has both training and generation all happening at the same time, and training and generation are completely different. And even for the generation here, the inference itself within RL, if you think about it, it's actually very different from online inference where you have to serve actual customer requests. But in RL, you are generating those responses only for training purposes. So it's actually not a latency sensitive inference workload. It's actually a throughput sensitive inference workloads, which is quite interesting in itself, right? So a lot of people looking at that. And finally, systems for agentic AI. So again, it's interesting because now you don't just have the LLMs, you have a whole lot of other things. And even if you just want to look at LLMs, they have to talk to each other. They have to share a lot of context. You have to make sure that they really do what you ask them to do, but don't do anything other than when you want them to do, and so on and so forth. And how you actually, how do you actually maintain this whole software engineering cycle for evolving these agents? You have to develop them, but then it's not done. You have to test them and then go back and debug and retest and so on and so forth. This whole cycle, how can you provide a framework that actually does that for the agents? That is also very interesting. But anyways, I've talked a very long time. So I should stop here. And I do think that it's a very interesting time to work on AI infrastructures and AI systems. And actually for students, in terms of finding jobs, and it's actually, if you work on that, it's actually really, really lucrative in terms of the packages that you will be getting. It's kind of crazy this year, but anyways, we can probably talk about that offline. But yeah, okay, with that, thank you.
Okay, fantastic stuff. So over to the audience. Do we have questions for Hong?
Yeah, really fantastic, keynote. Thank you very much. So I was curious for the root cause analysis. So you reported that the overhead was relatively low, right? And I was surprised because on the other slide you showed these measurements where you store the data in the database and like 10 terabytes per day.
Yes.
Was there any special trick to make it very efficient, or so why is the overhead so low? I was expecting much higher overhead.
So the overhead is, so we do have centralized components like the database, root cause analysis, and so on and so forth. But in terms of overhead to each of the device, each of the machine, it's actually just tracing, which is not that much.
Okay.
So we only, we're tracing at trunk level, but we only need to sort of aggregate every, I forgot what is the interval, but periodically aggregate these trunk level execution data, which actually doesn't create much of a overhead. So after that, we just push all the traces to the database, and so in terms of time that it takes compared to the training step time, it's actually quite small.
Okay.
Yeah.
And did you do any changes to the crypto communication protocols themselves?
No, we don't. We don't.
So just curious, do you think there could make sense to think about like in-network telemetry or like distributed communication?
That's true. I'm not sure, but I think they might have something like that.
Okay.
But again, I'm not 100% sure. But it's probably not like widely supported in the infrastructure, and that's probably why they don't. At least from what I know, they don't integrate this with Microsoft or other. Yeah. Okay. But they certainly have a lot of things just for the networking team that they look at incidents and failures. Okay. Yeah.
Any questions from the back?
Maybe also you're going short question about root cause analysis. It's still the questions there as well. I just feel like I'm not sure, like maybe in this year or next year, 2 years, with this new agents like OpenClaw and they have a very strong ability to calculate solution.
That's what we are trying to do now. You're right. So at the very beginning, we actually we've done something, but quite I would say it's quite rudimentary about troubleshooting with agents. So this upcoming FSC paper
Yeah.
where we so what we did is basically just to collect a bunch of data from Azure, their incident reports. So where we have the ground truth, but we also have the symptoms.
Right. So
Yeah.
I read that before. So
Right.
like just I mean, so in the agent type, like agent can not only analyze the logs, but even can add logs to the system.
Yes, absolutely. So that's what we are trying to do right now. So we want the agent to actually interact with the infrastructure. And then, for example, call a pin match. If the agent decides that, I need to get some information from pin match or whatever other monitoring tools that you already have, and then let me see that data. And then once I have that data, let me do some more analysis, and I can better decide, what is really the problem. Right. So that would be the next step. Yeah, exactly.
So how easy to do that the agent can do it?
Good.
I mean, the most naive, I don't want to ask about that. How good or bad it is?
I think so. I'm not too sure if when you give it a completely new problem, like something that none of the engineers have seen before, like it's a new problem when you have a new GPU or new hardware. I'm not sure how those agents would be able to handle that. When you give it something that it has seen before, or people have seen it before, then it should be relatively straightforward. But I think what's interesting is whether they can actually troubleshoot new problems that people actually don't have any clear knowledge about, and that's really fascinating to me. But right now, what we're trying to do is still to automate the process so that when you see failures that people have to address before, they have SOPs and stuff. Maybe you could follow that. At least you can read that and then sort of follow that logic and see if this is the same problem or not. But we haven't been able to. But it will be really exciting to see.
I guess you also want to balance the complexity of your logging versus the benefits of more fine-grained debugging, because you're already gathering terabytes of logging data.
Yeah.
So the deeper you go, the heavier the overhead.
Yeah. But for them in production, it's all worthwhile because you do need all this information. So when something happens, you can sort of point your fingers at the right person, kind of thing. So eventually, all this information is important to them. So they would rather pay that price.
But I guess the price isn't that huge if you step back from a moment, because the volume of logs you're creating is large because you're basically running thousands of GPUs.
Yeah.
But the actual volume of the individual logs per second is not huge because you're not collecting that. You could, for example, be taking huge memory dumps and condensing that into a log, but you're not.
We don't necessarily have to keep all of these things there. So.
Actually, no, it's not one question.
One quick question. So,
yes.
Your first work, I think you leveraging static.
Yes.
Do you also leverage detail training stuff for this moment for the content that's semantic?
Correct. So that's more from the codec kind of traditional codec kind of compression kind of point of view. Yeah. So we haven't looked at that, but I think it would apply naturally over here. But I'm not sure if people have tried that. My guess is maybe they have somehow. Yeah, but the reason there's more interest in sparsity and attention is because it's just for attention, which is not the same as traditional like codec, video codec and stuff. So that's why there's seems to be more interest in how sparsity actually plays out for attention. Yeah, I think for video there's a lot of opportunities here actually. Yeah. So I don't know if you know, but like 2 days ago, this new P2V model from CNES, CNES 2.0. So if you look at the clicks that they generate, it's ridiculously good. And you compare to the one that I showed you earlier. So yeah.
Maybe so agentic AI, right? It's very hot and so lots of attention, many companies and open source projects. I just wonder whether you could share some additional insights on what exactly you think would be the interesting research topics there.
Yeah. So I think there's a lot. I would mention one thing is benchmarking and evaluation. So this depends on what kind of task you want your agent to do. But no matter what task it is, in general, there's this lack of open benchmarking data sets or benchmarking tools, and even systems that would allow you to sort of try out the different agents, but for the same set of problems in the same set of environments in a reproducible way. So you could actually compare, like, scientifically compare and say that this agent is better than the others. It's sort of like LM arena kind of thing, so that once you have that, then you can perhaps start to iterate your agent design, get it better. Yeah, so that's actually something that we also want to do down the road. So that's one, and then there's also a lot of like context engineering problems here. So you keep seeing the agents that so their kind of workflow becomes more complicated because you don't have just one agent. You have most likely you have one sort of meta agent that makes all these high-level decisions. But then what it does is basically dispatch different jobs to different sub-agents. And then that sub-agent is going to work on different part of the things and then come back and so on and so forth. So you have to, there's a lot of communication, a lot of context window. Do you need all of them, or can you somehow compress, or I don't know, right? And so I think but that's a very important problem because it affects your performance, it affects the scalability of the system, and so on and so forth. And when you think about it, it's also fundamentally very interesting because right now we're thinking of still, in terms of context, we're thinking of hierarchical pairs and tokens and stuff. But that's really for natural language. That's really actually just for us because we need to read words and stuff. So we need tokens and so on. When you're talking about agent communication, do they really need tokens? They're not that. So there's even more things to. Yeah.
Thank you.
Great stuff. So I get the sense that was a lot of questions from the audience, but maybe we can take them over to lunch and continue over food.
All right. Thank you. Thank you.
Again.
Here is a visible asset. Go to the gesture.
So for those people on the online feed, all the physical humans are going to consume calories. We'll resume at 1:30 Hong Kong time, where we're going to have some mini presentations across the people who are physically with us today. Okay, welcome back. So first of all, welcome back to the physical audience. Hope lunch was enjoyable. I think we can all thank Zilly for his very, very generous lunch offerings. And welcome to our online audience as well. So we're really lucky because the next session is going to shake things up a little bit. And rather than going through some of the virtual presentations, we're going to give everybody in the room the opportunity to give their own 5-minute pitches. So this was something that was announced in advance, and some of you kindly proposed your names. So I have a list here, and we're going to keep it very simple. We're just going to take turns one at a time. We have time for Q&A, so if people want to raise a question, I think you're very welcome to shout out. So without any delay, let's invite our first speaker, Young Man Kim. Perfect timing. Wonderful timing. So in case anybody didn't hear before, this is the URL for joining the Zoom room. Once you join, you should be able to just share your screen, and then everybody online and physically will be able to see your slides. So, have you? Maybe a slight adjustment to the agenda. Maybe what we could do is go for Jan Bochum.
Maybe next slide is also not all right.
So, Yufan, ready?
Yes.
Yes, this is Yifan, and I'd like to share our ongoing project is about near surface design for AI glasses. So AI glasses is considered to be the next generation smart terminals with the capability of camera, display, audio, input, output, and so on. And one special thing is that the AI glasses enable the hands-free interaction between human and the machine, which is a very new capabilities. And also empowered by the emerging vision language models. So the AI glasses can be a host of your personal AI assistant. So our question is that how does AI glasses different from the current terminals like mobile phones? So for the capabilities, one special thing is that the glasses has limited battery because it cannot be too heavy to put it on your head. And then this result in the limited computation power on your glasses. And our requirement is that for applications, we need to again make it very low latency because we need seamless interaction between ourselves and our glasses. For applications like, for example, a real-time translation or AI video chat. And another good thing for glasses is that we do not need to have fancy UIs or file systems in the glasses. So in this part, we may do something to lose weight. So our choice is to use STM32 as a MCU and use Zephyr OS, a real-time operating system for the glasses. So for our glasses prototype. We use STM32 because it is very lightweight, power safe, and very cheap also. And we use Zephyr OS because it's a real-time OS. It's very lightweighted compared to normal operating systems like Linux or Android. So that's our development board. So we want to firstly develop on this board, and later we want to maybe cooperate with some hardware people to make it maybe like PCB redesign to make it like a glasses. So our optimization goal is to optimize the motion to photon latency. So here is an example of AI video chat on the AI glasses. So you can see that besides the latency on the influence of the large language models, actually there are also many components in the glasses that contribute a lot to the latency, like the camera buffer, encoder buffer, decoder buffer, display buffer, and the network socket buffer. So maybe because we are just at the beginning of this project, but we think that maybe we can somehow do some buffer design on the client or on the client device to shorten the latency on the client side. And here are some very preliminary results because I just made a board work yesterday. So it shows that for the low resolution, it works well and it follows the frame rate of 30 FPS. But if I increase the resolution, some latency goes up. So and if I increase to 1080p, maybe there's some bugs. So the network latency is over 800 milliseconds, which is abnormal. Okay, so that's my very brief introduction of our project of AI glasses buffer design.
Awesome. We have a minute for any quick questions.
Sure.
When you can time out the country having zero.
Oh yes. Actually, for these two parts, the calculated can be zero, but the camera hardware has a frame rate of 30 FPS. So when these two finish, the camera should wait for another 24 milliseconds to take another picture. You can see that if you add these three terms, it's about 33 milliseconds, which is the frame rate of 30 FPS.
So the capture time also considered as standard.
Oh, no, 生态系，生态系。
But if you only consider the encoder time, the
Yes.
encoder is 15 milliseconds for 7
Oh, yes.
and it is not match the 30 FPS interval.
Oh, yes. So I think the reason is that there are two camera buffers. So when I send something, actually another buffer is already here to capture the image. So after finishing, the buffer is already here, so it directly goes to the count.
Awesome stuff. Was there any other queries from the audience? Ideas?
Sure.
I think it's just starting, so I'm not too sure what is our research plan.
Research plan, maybe the first goal is try to optimize the latency here. So it is maybe there are some problems here. So and the general plan I think is maybe just to develop some kind of buffer design on a device. Because there are many different buffers in the camera encoder in web socket, web socket, and which may result in some internal latency. So I'm thinking if there are something can be optimized.
I have a quick silly question. Do these cameras directly connect to the endpoint, or is all of this going through the smartphone that's my tethered?
Yes.
It all runs through the smartphone.
Smartphone.
So like for many of these glasses, you don't have a SIM within it. It's not connecting to anything itself. Instead, it's passing all of its traffic through a smartphone that it's tethered to.
Oh, yes. It had to connect it all to a smartphone. Yes.
So for what you're doing, are you trying to work within that framework of having to connect via a smartphone? Or are you trying to build some new glasses? Because I think that smartphone connection is a big bottleneck, an obvious bottleneck at least.
Oh, let me see. So you mean the smartphone connection is a bottleneck?
Yeah, because you then introduce processing time on the smartphone device. Whereas if the glasses were to directly connect via Wi-Fi, you bypass that.
Oh, I think there's also a solution, I think. So we haven't decided yet, but I think it's possible for glasses to directly connect to Wi-Fi or even cellular network, and then to maybe large language model service. So bypass the mobile part. Thanks.
Okay, unless there's anything else, should we move on to our next speaker? So, am I safe in inviting Manuel?
So, and yeah, mentioned this is my research. It's called BD. So it's mainly doing real-time interaction in the theory mesh. So currently, yeah, theory mesh are using in some IoT environments. They are used for some low bit rate and control signals. And there is also some exploration in the community. They're trying to building decentralized peer-to-peer messaging apps and supporting multi-hop message. But I'm thinking so the fully opportunity is not fully utilized here. So maybe we can try to do some real-time communications and some videos, audios in the very mesh. So advantage of the VMware is very clear is a low latency and very low cost. So we can deploy it anywhere at any time very fast. So some simple example is such as the disaster recovery, different small drones, different small cameras that we can deploy anytime and can last very long with a small batteries. And also in some IoT environments that we can plug into existing IoT barrier networks. So the main challenge here is the routing algorithm. So the barrier mesh is using a flooding. That means one packet is going to flood through all the winning nodes, and that will not suitable for high bandwidth use. And there is also a high latency that we have to optimize for the connection interval because the BLE will schedule a sleep after each time they connect. And there is also limited bandwidth here. So I already implement an app that I mentioned earlier, a 2.5 videos or audio RTC. And the latency is here we can see it's currently very high due to the connection interval issues that I mentioned. Sorry. Yep, so you can see it's mainly 2 times connection interval, 4 times, and then 2 times. Okay. So and then the next step I'm going to do is I will try to modify the Bluetooth driver to adjust it to the for the real-time interactions and also optimize the encoders and video paths for the socket itself. And lastly, I will try to apply the logic.
Awesome stuff. Any questions or comments?
Thanks for what does the routing mean?
Routing is how the packet is delivered to the destination which not be passed through.
So it means that many barely divided like a mesh.
Yeah, it's a mesh. It's just like a network. There should be a routing table to be developed.
Oh, okay. Thanks.
So you also mentioned that you might need to do some modifications to the Bluetooth drivers. What are the particular bottlenecks that you're facing in the drivers currently?
So currently is how the packet is scheduled to scan. So for example, one big packet as it will split into different connection event. So if it is possible, it might be better that we can put one frame inside, or maybe one macro blocks inside one event. So the decoder can start decoding each in between the time it is resting before the next connection.
And part of my ignorance, I should know this, but when you say an event, what concretely is an event in this context?
So the event is the Bluetooth, they connect, like, for example, 11.25 milliseconds every time. So they will start sending the packet, and then they will send through packets, and then they will go to sleep for some time and then start again.
Great, okay. That makes sense. Any final quick comments or questions from the audience?
This is what we're talking about, that almost like our chat.
The next fire chat. Okay, so Jan, right, pop up. Okay, you want a few more moments to prep? If so, maybe we could invite Jia Yang up. For all the speakers, it might make sense to join the Zoom room now.
Okay, so today my talk is about our ongoing project, the XG glass. So what is this? In general, we provide a universal AI glass SDK to help developers to develop their AI glasses in an easy way. So we first talk about the background part. So currently, the AI glasses has a has a very has a commercial potential. It has been valued at USD 1 billion, and there have been many various types of AI glasses like Meta and Rocket and Reno. And we've also found that people can actually wear these AI glasses in their everyday life. Like the AI glasses act as personal AI assistants to perform like tasks like real-time translation or the navigation. And we believe that if the AI glasses are evolving to be a next generation smart terminal, it cannot live without these killer applications. So what are the killer applications? It means that these applications must be cannot live without the AI glasses. And we think that this should be like be done or be made better with the developer community. However, currently there are some challenges for the developers to develop their applications. The first is the scalability issues. So for this part, we can imagine that there are many types of glasses. Each glasses has their own SDK. That means that imagine that you write an application for one type of glasses. Now you may need to make this application to work for the another glasses. So you may need to move the entire code base to from one to another. That that takes a lot of time and efforts. And the second is that the SDK itself has a high barrier entry. The SDK currently, the AI glass provide has many low-level connectivities and interfaces. However, the application developers are from a higher level. So, so the developers cannot try to master the both low-level skills and high-level skills. And current solutions like the OpenXR or the Metro OS, we've found that they also have some shortcomings. So for the OpenXR, it is for the AR or VR, this kind of stuff. However, it is too complicated for the simple AI glasses logic. And while the Metro OS, it is an OS-related solution. So it requires the glasses has the certain type or version of the hardware. It is cannot be modified easily from like application level. So let's talk about how we design this SDK. So our goal is that we provide developers one code base, and developers utilize this code base and can be adapted to every type of classes. So in our SDK, we support different types of classes like standalone or the phone tethered. So what are these differences? So for standalone, you can treat these AI classes as an independent phone, like an Android phone, while the phone tethered glasses, it needs to be connected. The glasses need to be connected to a mobile phone, and the mobile phone transfer or receive the commands or and receive the like the images or the audios from the AI glasses. And we also handles this connectivity internally in our SDK, like the Wi-Fi or the Bluetooth. And we currently provide these four types of features. The first is the capture photo. So the AI glasses have its own camera, it can capture photo, and the second is the audio record. And similarly, the AI glasses use their microphone and display text. So currently, the AI glasses have some small or tiny monitor in the lens, and can display the text to the users. And the final one is the audio play, the speaker of the AI glasses. And with this four types of the interfaces, we believe that the application can be done with these interfaces, and we make it easy for the developers to write the code or write the whole project in a very easy way. Developers only need to focus on the application logic and don't need to worry about the low level connectivity or the different types of glasses, which SDK he should follow. And we also provide an example. So for this, you can take the left picture. So for developers, they may like write a code translation application. So in this application, it is very easy. So the AI glasses took a photo, and it like transfer the photo to a remote AI service, and the remote service returns the translation results to the user. And the result actually will be it is on the AI glasses, the monitor, and the user can see the monitor. So what does the developer do? So he can simply write this code in NINES code. So actually we use the interfaces like the capture photo and display the text. And after this, he can run this single file use our command tools we provided, and after running this, we can you can automatically packages and launches app on their like Android phones. And through this application, we can make our glasses to perform as a translation assistant. So, and this is my presentation.
Really cool stuff.
Quick question. Wouldn't the latency quite noticeable when you issue these ChatGPT prompts? So compared to when you have translation services, right? You want to often have them very quickly, very fast.
Yeah.
It does not incur a little bit of maybe too much latency.
Yeah, we actually measure the latency. So for the GPT 5.2, and it is actually real end, and it has a latency of around the time to the first token, the latency around 2.5 seconds. And for other models like Mistral or some with a smaller sizes, and we found the quickest one can be over 1 second and below 2 seconds. So indeed we think that this can also be a optimization direction, and we are actually it's also another ongoing project to minimize this.
Other questions from the audience? So maybe a quick question for me. So if I understand correctly, you're essentially creating a shim around the SDK. So you've got your wrapper with your standardized interface, and that sort of gets mapped into the respective interfaces of these different SDKs. How heavyweight is managing and maintaining this? Because I guess with time, the different SDKs will evolve.
Yeah,
they'll change, and you'll need to also change your respective implementation. Is this like a huge engineering effort, or have you got some like tips and tricks about how you streamline the process?
Yeah, I think that it needs much effort because different SDK may involved, and actually like there has little tricks also like these things. So I think I also like make this project open source, and we want like more contributors to contribute to this project. Yeah.
Am I right in thinking that you were manually reviewing the code and doing the mapping yourself, or was there any automation there?
Yeah, currently we are like manually reviewing the code. We like to investigate how this SDK of a certain type of classes work, and we try to merge it into our SDK.
Because I was wondering, I apologize in advance to everybody for this comment, but maybe this is the type of task that an LLM could help facilitate, because as the SDKs change, you could maybe task an LLM with doing the mapping function for you.
Yeah, I think that's very useful. And currently we in our general like coding, we actually utilize the LLM. But if we want LLM to directly to immerse one SDK into our SDK, so we also need to make sure that it did not run. It is correct. So I think that it is a useful solution that we can think about. Yeah.
Awesome work. Any other final comments? Let's thank our speaker then. Now the moment we've all been waiting for.
That's incredible. That's screenshotting.
Hello, everyone. It's my great honor to share my idea about. Okay. Let me share my idea about uploading technology with NVLink chip to chip. And this picture shows the block diagram of GB200, and in this GB200 system, the NVLink chip-to-chip connection between the Squeeze CPU and the Blackwell GPU is about 7 times faster than PCIe. And 16 slot PCIe link provide up to 64 gigabytes per second in one direction, while NVLink chip-to-chip provides up to 450 gigabytes per second. That's my idea is offloading would be a very promising feature in this system. And in recent year, 3D parallelism, including DP, TP, TP has become the standard for model pre-training, and the pipeline parallelism introduced bubbles due to data dependency between stages. And I'm trying to shuttling model status layer by layer between CPU and GPU in a ping pong fashion. And by offloading the model status to CPU memory, maybe we could fit the entire large language model on one or two GPU without requiring pipeline parallelism. And we think with proper scheduling, the communication can be overlapped with computation, potentially avoiding bubbles. And however, the CPU's relevant modest performance might make it difficult to offload optimizer computation to the CPU as done in framework like zero offload. But it could be but it can transport the data, upload the data to CPU, and support loading data to GPU. And uploading may allow us to increase the micro batch size. It's known to us all. In many cases, we set micro batch size to equal to 1. If so, the resulting increase in computation and density could help elevate some of the CPU overload. Thank you.
Awesome stuff. Audience, questions?
How large is the CPU memory?
It's more than 1,000 gigabytes.
1,000 gigabytes.
Yeah.
Terabytes.
Yeah.
So it's much bigger than GPU memory.
Yeah.
So we need to upload something to CPU memory.
Yeah. We upload the entire model to CPU memory and load it when we require to compute in GPU.
Oh, okay. Thank you.
To our audience, any comments, questions, ideas?
So many upload the model parameters to CPU memory. What about the cache?
We offload almost everything to the CPU. Yeah. So we hope to increase the micro batch to a much more large number. So we try to offload everything to CPU and reserve much more space for large micro batch size.
Okay, unless we have any other questions, let's thank our speaker. Fantastic. Fine.
It's a little bit slow, okay? Hello everyone, my name is Hua, and I'm a student from Professor Mo's group. And this is our ongoing project that is called Socket Codec. We want to achieve the consistent low latency in real-time communication. So this is a very basic pipeline about the current RTC. I want to first introduce what is socket and what is codec. So the codec includes the encoder and the decoder. That is the encoder to compress the original big data into smaller size, and the decoder is to decompress it. After the encoding process, the encoder will give a whole encoded frame to the socket, and the socket will divide it into smaller packets to transmit. This is the whole process about the RTC. So our proposal is we want to combine the socket and codec. And why? Why we want to combine? First, I want to dive into the detailed transmission process about the RTC. There is one key feature about the current RTC that is bursty things. So the basic pipeline is like this. So the encoder encoded a whole frame that is maybe something, of course, it's larger than the packet size, and pass it to the transmission that is a socket. And here, currently we have the pacer in the socket, not in the socket, above the socket. Why we need this pacer? Because the frame size is a bursty. If we do not manage, we just to send out them, it will cause the network very busy. So we have the pacer. We want to smooth this large size send out. We want to send packet by packet. This will smooth the flow, but what happens is here happens a bandwidth drop. If the sender cannot react very fast to this drop, this will cause a huge delay spike. So currently we have two dimensions optimization about this. First is about the congestion control algorithm, including the Pudica, the COPA, the latest congestion control algorithm. That is to try to faster respond the bandwidth drop. And the second dimension is about the encoder. And this is our previous work called MAE. We indicate that the encoder, even though the CCE can react very fast, but the encoder it has the 5 to 7 frames to adapt to the new bit rate. So this low reaction also causes the delay spike. But this is a current pipeline. What is the bottleneck or the lower bound about the current latency? That is, even though our congestion control algorithm can react very fast, even the one RTT after the bandwidth drop, the encoder can only react in the next frame. That will cause the remaining packet of current frame will overshoot. And current, because the bandwidth is usually high, for example, for 30 Mbps, it will contain the 300 packets for one frame. That means maybe we have 200 packets will overshoot the current network. And we have a very basic simulation about, why we will have this, because the network is is packet by packet, that is single packet, but our encoder is a grouped packet. We have a basic simulation about what will cause about the grouped packet. We can see that for the RTT, the relative low, that is 10 or 20 milliseconds, the grouped packet will cause 6 or 7 times about the single packet. And here we will have a huge gap, and this gap cannot be solved because current codec is naturally grouped packet. So our idea about socket codec is very naturally, that is, we divide the whole encode process also into this smooth and have the interval process. That is, we not to encode the whole frame at the first time, and we just to divide them into a very relative frame interval. This maybe the packet interval, and here we can have a very immediate react when the bandwidth drop happens. The CCE sense that the current has a drop, and then the encoder can immediately react to achieve the real consistent low latency. Okay, thank you. That's all my presentation.
Good stuff. Okay, audience, we have questions or comments.
Can you firstly encode and separate into two sections?
Sorry.
Can you first encode?
First encode.
Yeah, first encode everything, all frames and then send them at efficient speed to frame size and then transmit them.
Oh, you mean the SVC? Yes, you provide different level of frame size, and based on the current network to transmit different. Okay, they have two disadvantages. First, SVC will have an encode overload. It will reduce the encode efficiency to achieve this level, the hierarchical structure. And this will reduce finally reduce the quality. And the second is we cannot predict the network. That means when we encode the three levels, for example, the three level different size, we cannot know the detailed network. So we cannot provide the very accurate frame for the current network. It may, for example, the second level might a little bit overshoot, but the third level is much more smaller. It's very hard to provide very detailed or accurate control. But in this way, in the socket codec, we can to have the very accurate about the network control.
Right, so can I have politics, politics.
I think it still will make the previous problem that how do you to provide the how do you provide the network really need this screen size? Because for example, you only have the maybe 3 or 4 or 5 these different qualities, and they have different screen size that is different target bit rates.
I think we all want to work to
We can because we are not to predict the bandwidth and pre to generate 3 or 4 different levels. We are to react after the bandwidth really drop. Then we can get the current network state. We can know the current bit rate about the network. Then we change accordingly.
But I think essentially we want to time that is involved in the process.
To be honest, you mean
so then what first. Then we can just involved in the process.
Oh, there is one thing that the encoder to reduce the encoded bitrate is not time consuming. It can quickly to reduce it. So this is not time consuming. That means if we tell the encoder to encode at a lower bitrate, it can immediately to react. Thank you.
Awesome stuff. So this morning, our first presentation was by Dave Clark talking about decentralization, and Heather, as the chair of the NRG, kindly agreed to do a slightly extended talk this today.
Yeah, thank you very much, Zilly and Gareth, for organizing this NINeS pod. It's really great to see so many people interested in really cool networking research, systems research. And yeah, and so indeed, like about 7 years ago, I started the research group on decentralization of the internet in the Internet Research Task Force, because at that time, yeah, these trends that Dave Clark talked about earlier and the detrimental consequences were already quite obvious. And so we thought, okay, what could we possibly do about this, for the future evolution of the internet? Now, if you listen to what the people say that build the internet, and also the companies that massively profit from the internet, so there's lots of folklore, those like nice stories, right? So the internet is for the end users and so on. This is actually a good document that is critical about some developments. The reality, though, is, I mean, we, the users, right, the people, are actually not really the biggest beneficiaries of the internet. In reality, we have something like this, right? So the so-called ecosystem of data economy, tracking every move, aggregating our data, reselling our data. So most of the big companies, right, so that we kind of trust
They always claim that they have data protection and privacy rules and so on. In reality, they are buying the data from many smaller, maybe not so exposed, tracking companies that are basically monitoring us all the time. And so this has severe consequences in terms of who's actually in control. So if I know everything about Zilli, it's very easy for me to steer his next day's purchase decisions, maybe political decisions, whatever. And so that's a real risk for societies. And so the question is, how has this actually happened? And so Dave Clark also referred to the change in the internet architecture this morning. So this is what you would normally learn in Networking 101 in the textbook, right? So that we have the decentralized internet, there's no center, there's maybe a hierarchy of ISPs, so this is partly German, it's actually from the textbook. We have regional ISPs and tier one ISPs, and there would be mostly, non-paid connections, but then where you want to kind of get data from like tier one ISPs, you would have to pay for them. So it's a kind of the money flow was kind of well understood there, and it kind of worked in some way. Now, we all know that the internet does not look like this anymore. So today, we're not so interested anymore to talk to a remote host somewhere in the internet. What we want to get content. We want to maybe get some interactive Zoom service or something. We typically never talk to these servers directly. We talk to CDN infrastructure and other intermediaries, and they are coming closer and closer to us, to the edge of the internet. So we all know that. Right? So nothing these days works really without CDN, and there are several companies, and the big companies, they run their own CDNs, and they have a lot of decision power. Who gets to run these instances, where ISPs can put these instances, and so on, and they can use them for many purposes. So now, in reality, that means this whole peering infrastructure is also effectively changed. So effectively now, the CDN is basically the new core of the network. And CDN operators, application software, they dictate where these CDN proxies would reside in an ISP network and so on. It doesn't have to be that thing necessarily, because many of the services that we all like and use every day, they kind of need something like this, but it just illustrates also a shift in architecture and control power. And so today's network is more like a service delivery network, and it's not like yesterday's internet. So the new end is basically these proxies. So we can now pre-provision services to multiple network locations without no problem, like local to users, fast access, and no assumption of end-to-end connectivity anymore. So that entails profound changes. So we have now much more capacity in the network, so we can do many cool new services. And well, with the advent of AI, you can imagine there will be more services like that in the future. So there's more demand that also then creates more edge infrastructure. So it's a kind of productive cycle in a sense. And so the more we do this, then this economy of scale sets in, and this also then reduces the cost of carrying in edge networks. So today, the cost of shifting data there is almost, you cannot really quantify it because it's so low. And so previously, many people tried different attempts on decentralizing the internet again, to make it possible also for small players to roll out services easily, to have more user-controlled communication, avoid tracking and all these things. So some of you, I talked to some of you earlier, know a bit about Web3, for example, right? It was also it's a proposal to decentralize the web. In reality, you have to admit, right, these attempts have largely failed. So people try to
also use blockchain to decentralize certain internet services, maybe name lookup or some routing infrastructure and so on. That's all failed. And there are a couple of reasons, but so one reason is also certainly that many of these systems are actually not as decentralized as people normally assume. So there is a study here on the right-hand side, Cloud Strikes Back, that analyzes this. And yeah, so there was a big movement to try to achieve something there, but in my view, just sprinkling some blockchain dust on the problem is not really helpful. So it's a bit like, religion in some way, and it doesn't really solve the problem. And but what we learned from analyzing these, let's say, failed attempts is that so there are many interpretations of what does centralization actually mean, right? So is it infrastructure, but is it money? Well, fundamentally, it's centralization of control. So that's what these big companies now are able to exercise. So they have centralized control powers, and they have a lot of influence. Also, like how when a work develops, how decisions are made in standards organization, political systems, and so on. And so you can name a few factors, perhaps, or you can investigate what could be the factors. So it's quite interesting to study this a little bit also with the history of the internet. So it was constructed as a foundation of a market-based economy, like not a command and control economy, but really purposely designed like a market economy. And it was assumed that open market-based activity would generate efficient outcomes based on competitive pressures between those providers. And it has worked for some time. But yet now, the internet is not really a highly competitive environment. It's strongly consolidated and not very competitive at all. So these are thoughts by Jeff Houston, one of the contributors to our DINRG group. So the question is, what's driving this evolution in the internet basic architecture if competition is not the main factor? And so we are asking ourselves, right, is this, are there technical issues, or technical evolution aspects? Is it just normal economic concentration like everywhere else? Or did we make some mistakes when we designed the internet? And so there are certainly something also that has to do with technical evolution, right? So just Moore's law has it made possible for many, many years to just always double and increase like hardware installations without like doubling the cost in the same way. So we have an abundance of processing, storage, communication that makes it very easy to come up with like this, caching, CDN, application proxies, infrastructure. That's certainly just a trend that we have to accept. Then economic concentration, you cannot deny, right, that there are trends like in all other industries, but in the internet it's even stronger, right? So in the internet you can produce extremely high profit if you manage to position yourself as a monopoly, and this is what many of these companies are trying all the time. So you may have read this Peter Thiel piece, competition is for losers. So that's exactly laying out the strategies for internet companies. And then you can also ask, okay, so what are there maybe some design problems? So the internet has grown very fast in the beginning. Maybe some mistakes were made or some things were ignored. And that's also true, right? So if you think about how security, for example, was developed, so nowadays it's very hard for us to communicate securely directly, right? So we never do it. We always go through some intermediary. I'm not sure who of us is hosting their own mail server, their own web server, or something like that. Nobody does this anymore because it's so complicated to get this right? And so that's and the reason for that is also has to do with how technology has been designed. So web security has been kind of added on later just to enable e-commerce. And when this was done, people were interested, okay, we need to authenticate servers. We don't need to authenticate the users with the same mechanism. So you need maybe an account, username and password, that's enough, but you don't need trust anchors, you don't need stable identifiers and so on. And this also naturally leads to a shift where like server, cloud-based platforms and so on, they can provide secure services. We cannot really do this easily. We understand the alternatives there. So if you, for example, had a system where each of us had identities, we had trust anchors, we could set up communication sessions directly, we could host our own services maybe easier. It's not, of course, also not trivial, not easy to implement. It kind of connects to what Dave mentioned this morning. You also have to think about how people would use that, right? So non-experts need to be able to do this as well. So I would agree there's also a usability HCI problem there. So some takeaways that we learned is that, I mean, there are really strong forces towards centralization, and we cannot really revert to the, day one internet anymore. But the question is, can we control it somehow? Can we maybe induce some change to the better? And I think, yeah, there is potential, but you really need this cross-disciplinary approach. You need to understand not only technology, you need to understand economics, first of all. You need to understand, how policy making, regulation can actually work and affect change. And then also need to understand how users think, so psychology and HCI. So we wrote a report on some of our insights some years ago. And so what we're trying to do is to create building blocks and enablers for design system design. We cannot really force anything, but the hope is to also create some knowledge that application developers can benefit on, but also policymakers and regulators. So if you want to, regulate something, you need to understand, right? So what are the technical boundaries? How would this affect the so-called ecosystem and so on? So it's non-trivial. And so today I'd like to issue a call to action. So I'd like to advocate a principled approach to decentralization. So based on a really comprehensive understanding of the technical factors and the economic factors. And then do more research on like building blocks that can make a difference. So I talked about names, identities, and trust anchors. So maybe most people would think that maybe we don't need direct communication anymore these days. I would agree, but still being able to do this enables a whole different perspective on how to develop communication servers, especially in this age of agentic AI, for example. So enable service provisioning without these centralization choke points. And then, yeah, definitely think about economic models. So what could be incentives for people to develop such applications, to use these applications? And as what Dave also mentioned, what would be actual money flows or business models? And well, nobody wants to pay for things. And well, unfortunately, like there are not many companies who are willing to offer services if that's the case. So there needs to be a new way of thinking there. And so this is not something where you can do like a top-down radical decision. So I think what's needed is a smart approach where you can, step by step develop better technology, educate policymakers, regulators, and then provide incentives for developers and users to make a change. And so if you're interested, then I invite you to come work with me on the future of the internet in the Internet Research Task Force. So the Internet Research Task Force, IRTF, is the global forum that works on different topics on advancing the internet. So not only centralization, but also all kinds of relevant topics, quantum communication, AI, so infrastructure for AI, security, and so on. And it's a really good opportunity to combine your research with activities that can really make a difference. So if you want to make some impact with your work, I would like to tell you more about how this would work in the Internet Research Task Force. There's a very good opportunity for you to do that because so the IETF, which is like our sister organization that is hosting us, will have a meeting in Shenzhen in the middle of March, so 14th to 20th. And for students, for example, it's quite affordable to attend these meetings directly on site in Shenzhen. And before this IETF week, Professor Mang and I are hosting the HKUST Internet Research Workshop also in Shenzhen. That's on Friday, March 13th. And so we have done this a couple of times, and it's a nice forum with like really a discussion-oriented forum to discuss new ideas. So a bit like our little session just right now. And so everybody's welcome to come give talks or ask questions and participate in the discussion. Thank you so much for your attention.
Great stuff. Any questions or comments from the audience?
Assuming the decentralization of the
Let's say, yeah, I'm getting this question. So the question was, it looks like you are assuming decentralization would be good. And that's, it's a good point. So we are getting that question as well.
So except for the obvious, like the democracy, like that kind of mindset. So what is the real benefits that users can benefit from the decentralized system?
Yeah, so we saw this one example with the SDK for developing the smart glass application. Right? So right now, well, the innovation in the internet is also a bit stifled because none of us can really come up with new ideas easily, roll them out as the permissionless internet was designed to. So that would be another benefit. So we would make it easier to develop things, deploy things securely. Of course, it's easy to put up an app that just doesn't consider security. But if you want to have a robust system, you need to think about security. If you want to make this easier and less centralized, then you have to think about other approaches. So identities, trust anchors for everybody.
But if we think about, so let's assume all nodes are equal, and they are naturally interconnected.
Yeah.
And there is a decentralized system. But gradually, some of those become more powerful. And then, in that sense, because of the value of all of these entities, they can naturally grow. And in that case, some of the systems would generally be centralized. I think that is the trend.
Right. So let me just repeat the question for the remote audience. So the question was, comment was, well, even if the internet was decentralized, there could be a trend that the popular applications or service providers would grow, and then you have a slow trend towards centralization again. Right. So that's why I think this is not only a technological problem, but it's a societal problem. And of course, societies need to decide, how they want to deal with this, let's say, industry and so-called ecosystem. And of course, you need a certain scale also to provide efficient services. So it's not like everything should be totally decentralized. But as also in other sectors, in other industry sectors, you don't want to have such a high level, high degree of centralization and control power concentration that basically somehow then the companies are more powerful than the government or the society. And so, as in other sectors, we need to find ways to regulate this. And the question is, you cannot just do a top-down decision. Okay, let's just destroy these companies or split these companies. I think we need to have smarter, maybe smaller mechanisms. Also to create competition, encourage competition, and but I think there should be a discussion how this should be done best without throwing away all the good properties of the internet. But so your points are really well taken. Yeah. Thank you.
Great stuff. Any other questions or comments from the audience? Well, we've hit the coffee break, so let's thank our speakers and let's thank all of our speakers. So for the benefit of the remote viewers, we'll be breaking for a physical coffee break and returning in about 25 minutes' time.
Okay, so hello everyone, including ones from the online and watching this live stream. We're going to start with the next sessions, and then we are going to have the more papers to watch and later discuss based on the paper recordings. So let me share the screen first. Share some. Perfect. Oh, I think there's a choice of sharing optimized for video sharing. Okay, great. So the first paper that we voted that we are going to watch is the Orbital Brain, a distributed framework for training ML models in space. And authors are from the MIT and Microsoft Rice. So let's take a look what the authors are doing here.
Hi, I'm Om. Today I'll be presenting Orbital Brain, Harnessing Distributed Training in Space. This is a joint work between Channing, Kevin, Santiago, Ben Naz, Peter, and Renvier. As we've seen over the last few years, the resolution quality of satellite imagery has gotten extremely precise. This imagery has been used for numerous applications ranging from forest fire detection to flood detection to even normal just agricultural monitoring. And as time goes on, this resolution continues to increase. For instance, on Planet's newest satellite class, they're aiming for a 1 meter resolution. And these satellites are starting to become equipped with high powerful GPUs like NVIDIA's GPUs. And as this resolution goes higher and higher, what you'll see is that there's an explosive amount of growth in the amount of data that these constellations are capturing. So for instance, here on the left, I have a plot on the number of satellites that Planet has. And what we've seen is that it's exploded to nearly a few hundred satellites that are continually capturing photos every day. And on the right here, we have a graph showing the amount of data that each one of these satellites captures. And we're nearly at the point where they're capturing 25,000 photos a day. And increasingly, as this graph continues, the amount of data in each one of those photos is also increasing. So as a result, we're seeing an exponential growth in the amount of data that this whole entire constellation captures. So if we just look at one singular satellite, let's explain what happens. So as the satellite is traveling across the Earth, it'll continually capture all of these photos. And then whenever it comes into contact with the ground station, it'll start to downlink a lot of these photos that it captures. At one point it's downloaded, these images will be transferred to the cloud where some model can be run, and then increasingly a user can access them. However, what we'll see is that this downlink from the satellite to the ground station is becoming extremely constrained to the point where this is not simply scalable to the amount of data that's becoming. In fact, as we zoom out to the whole entire constellation, you'll see that all of these X's here are satellites, and all of the green are obviously ground stations. And what you'll see is that no matter what happens, there's a constrained downlink between the satellite and the ground station. And what you'll see here is that this is really the core bottleneck. And so even if we apply compression, which in this case we use 3x compression, which is the state of the art at the time of this paper, what we saw is that only 30% of the captured data reaches the ground. And even if you were to deploy new ground stations or new compression algorithms, this is only a very linear scaling. So here in Orbital Brain, we asked a very natural question of, can we do everything in space? So increasingly over the last few years, we've seen so many papers which can push inference to the space of how can we run models which detect, say, forest fires on the Earth. And here we asked, can we even train those models in space? And can we just run everything in space? And there's hopefully, at first you might be saying, why are we doing this? But hopefully here with the motivation, I can convince you that this might be a possible solution which can happen in the future. And so what we're seeing is that, one, all of these new satellites are being equipped with increasingly more and more powerful compute. Two, these satellites are equipped with stronger and stronger inter-satellite links. Three, all of these satellites are run by one or two organizations which allow for permissive capabilities. And four, these satellite orbits are extremely predictable. So one, let's talk about why there's more compute in space. Increasingly on every single one of their satellites, Planet Labs and other similar satellite operators are adding GPUs to their deployment. The default case is, say, an NVIDIA Jetson GPU, which is just a small low-cost GPU, which is designed for, say, mobile devices. Increasingly, we're even seeing, though, H100s being deployed on these satellites. For instance, they just launched a test one with one of these. And this is motivated by a lot of reasons, specifically because the more compute that you can do on space, the less you have to transfer to the ground. Similarly, we're seeing that intersatellite links, which are basically lasers that allow one satellite to directly talk to another satellite just over the air, these are increasingly becoming deployed, and they allow for substantially more amounts of communication. So here on the left, for instance, I plotted the ground to satellite connections for the whole entire constellation over the day. What you'll see, though, is that there's maybe on average around 15 to 20 satellite GS to SAT connections. And once you consider energy, it's under 10 on average. Now, on the other hand, if we look at the amount of satellite to satellite connections which are possible, you'll see on the order of 10,000 satellites, of 10,000 connections are possible. And even if we consider energy, you'll see that it only drops to around 5 to 6,000. So these allow for much more frequent communication patterns, unlike the ground to sat connections, which you have to make many hours to connect to. Similarly, what you'll see is that while intersatellite links have a much higher bandwidth, much higher variance in the bandwidth, the maximum intersatellite link communication is much more than a ground to sat, because an intersatellite link has an uninterrupted laser communication as opposed to having to go from space all the way down to the Earth. Similarly, what you'll see is that satellite orbits are extremely predictable. Because they're following a fixed pattern around the Earth, which is governed by physics, they cannot move and deviate substantially from their orbit over the course of, say, 5 or 6 hours. In fact, previous studies have found that even though they're at so high in space, they can be predictable to a few kilometers. And as a result of this predictable in the orbit, you can also predict many other downstream things. For instance, energy is extremely predictable because it just has to deal with whether the satellite is in view of the sun or if it's covered by the Earth. Likewise, link data rates are also extremely predictable because it's mostly a function of where the satellite is relative to the ground station. And those can be predicted to 1 or 2 dBm. Finally, what you'll see is that there's a highly constrained budget in terms of energy. A satellite only generates around 7 watts of power from their solar panels. Now, downlinking all the way from space to ground takes around 50 watts. And similarly, if you were just to run your GPU, this is NVIDIA Jetson, with an intersatellite link, it only takes around 7.5 watts, which is much cheaper in terms of power. And finally, what you'll see is that storage is limited. So onboard storage limits force you to make decisions because there's only 360 GB roughly on board. So you can't keep storing all of your data across a whole entire day as you start doing as you look at the full constellation. So then we present Orbital Brain. So Orbital Brain is a new scheduling framework which allows for distributed training to happen in space. In Orbital Brain, there's 3 possible decisions which a satellite does at each window, which is roughly every 5 minutes. 1, a satellite can do local compute, which is that it can take all of these samples that the satellite itself has collected and train on those locally. 2, it can do model aggregation, which basically will take all of these different satellites as local models and combine them together. 3, we allow for data transfer, which basically allows raw data that a satellite takes to directly transfer with another satellite's raw data. So let's first talk about who actually runs what in Orbital Brain. So at the first is the core, which is our cloud, like a data center on Earth, which runs a scheduling platform, which will then get which will then get uploaded. Our ground stations act as simply a relay, which they forward control messages whenever a satellite comes into pass. And then finally, satellites will execute their assigned decisions by the cloud. So just to reiterate this, if we look at the data flow on the left here, whenever in contact with the ground station, the satellite will send their local model updates, their energy and storage status, and any updated images that they'd like to send to the ground. The ground station will send a new compute schedule and a new data model transfer schedule up to the satellite. And then the satellites will execute and transfer data when scheduled by that platform. Similarly, if we look at the scheduling framework, which runs on the cloud, there's 4 steps. There's the performance profiler, which happens every single time a satellite comes into contact with a ground station. It'll basically send some profile updates, which will then be used in a future scheduling framework. There's a model aggregator formulator, which basically will formulate when satellites should share models with each other. There's a data transfer formulator, which will decide when satellites should send raw data with each other. And then there's an executor, which will combine all of these. So first, let's talk about the first step, the performance profiler. The idea is that whenever a satellite comes into contact with the cloud, the satellite will download all of these data. For satellites that are not currently in view, the cloud will keep an update based off of when it was previously in contact and basically update locally an estimation of all of these variables. So one, we have staleness, which is basically when was the last time the satellite had their model aggregated. Two is the samples that they used. Three is the predicted compute, basically how much energy do they likely have to perform training. And four is the last observed loss, basically what is the local training loss. Then once we have this performance profiler, we get into this model aggregation mechanism, or MA mechanism. The key idea here is that we want to use ISLs to keep these models fresh and up to date from each other. These non-ground station satellites will participate in aggregation through routing through these ISLs, and this allows communication across the whole entire constellation. So let's first get into when we should perform local compute, and that'll inform when we can perform model aggregation. So let's first ask, when is it most valuable to actually just train on the data? So it's most valuable whenever one, they have a lot of data, and two, they have a lot of energy, and two, they have a lot of samples which are far away from the current model. However, if you have a very old model, it's not beneficial for you to spend your energy local training because you're just going to be fine-tuning a very crappy model, which is not up to date with the whole entire constellation. So then we get into this idea of when can we balance compute versus model aggregation. And the idea is that we only want to do model aggregation whenever it's actually beneficial over each satellite doing their local compute. And this is determined by the average staleness across the whole entire constellation and the amount of energy spent to do this aggregation. And so the idea is that we want to allow this constellation to first do local training, and then as time goes on, aggregate their models more. And what you'll see here is that because of this model aggregation, we're able to reduce this thing called staleness. So on the x-axis here, we have staleness, which is the number of windows of a satellite having the local model updated. And on the y-axis here is the CDF. And what you can see here is there's about a 4x improvement in staleness once model aggregation occurs. So then we get this idea of data transfer, which is that we want to fix non-IID, that is independent data at the source. So basically what you'll see is that since each satellite has a fixed orbit, every satellite will overfit to their own local data distribution. So for instance, here we have a 60 class classification task. I'll get into more details in the eval section. But what ends up happening is that over the first, let's say 1.5 hours, they'll only collect 30 or 40 data labels. And as a result, if they were to train on that, that would end up overfitting to their local data. And this is not beneficial in terms of energy and compute. So to do this, whenever a satellite comes into contact with the ground, they calculate the JSD. That is, we calculate a number representing the IID distribution. Then the cloud will basically calculate, based off of that satellite, every satellite they can come into communication with, what's the actual beneficial for it to be transferred. And then finally, we basically will take all of these links and determine whether or not the transfer utility is actually better than just spending that energy on just training the model itself. And what we'll show is that we only do this whether it's actually beneficial over just simply training on your data. And what we'll see here is that by actually using data transferring, we're able to reduce the average IID across the whole entire constellation. So then we get into our experimental setup. We use TLE traces from planet-inspired constellations. We use link and data rate modeling that Planet has released. We use energy and storage also from Planet data. And then here on the slides, I'll report results from FMOW, which is a 60 class classification class, but we have more tasks in the paper. Let's first look at the final accuracy. What you'll see here is that bent pipe, which is the normal way of just downlinking data to the satellite, produces around 47% and 50% on Spire. However, Orbital Brain is able to beat this by 52% and 59% respectively. Similarly, if we look at the time to achieve the same accuracy as BEMPipe, we'll see around a 1.55x and a 1.52x. So basically we're around, what used to originally take 1.5 hours now takes around 1. And finally, we show an ablation study. What you can see here is that whenever we disable model aggregation, we'll lose around a 15% accuracy. And whenever we disable data transfer, we'll lose around 11% accuracy. And in both of these cases, we'll have a slowdown of 2.5 and 2.2 respectively. Thank you for listening.
Hi, I'm Alex Krenzel from UC Berkeley.
Great. Any questions from the audience? Any comments? Anything you want to share?
I have perhaps two questions about the topic relevance. How much money does it cost to put additional equipment in space? Because my old-fashioned understanding was that for all of these satellite launches, they try to minimize as much as possible everything they put on because
we'll have a
costs like $10 trillion extra dollars. I'm wondering what's the cost-benefit ratio again?
Probably my view is that the cost for launching them into the space is already comparable with the cost of chicken.
So
OpenAI is going to commit $1 trillion to buy it. It's already $1 trillion with $1 trillion.
Yeah, again, I don't know the topic well, but I guess all of these satellite launches are going to become so commoditized that you just, as an individual company, and license and make a decision of how much you're willing to pay versus put up there. And I guess for different types of satellite deployments and different applications, you might make a different decision. Doesn't UST have a satellite, right? No, I'm sure.
Like UST does have a satellite, but that was it's just like from the type of co-development in our university. It's not led by the UST.
So we just stole the PR.
That's very interesting.
Just a look. Yes. What's next on the list?
Okay, then the next from list is utility-aware parameter allocation for cloud-augmented autonomous control from UC Berkeley. Oh, great. So let's take a look at the video now.
Hi, I'm Alex Krenzel from UC Berkeley. And in this talk, I'm going to present our system, Turbo, that does real-time utility-aware bandwidth allocation to enable self-driving cars to use the cloud. Now, we started this work from the observation that there was a persistent and widening gap between the compute available at the edge on self-driving cars and in the cloud. State-of-the-art GPU performance has grown exponentially over recent years. But these new chips also come with serious infrastructure requirements. At the same time, cars have constraints that severely limit the compute that can run on them, including energy, stability, cooling, space, and perhaps most importantly, cost. An H100 chip costs about the same as an entire Tesla, which offers self-driving today. So taken together practically, the state-of-the-art GPUs available on the market today offer over an order of magnitude more compute, more flops, versus the best on-car GPUs available today. The trouble here is that ML progress has largely turned to model scaling in recent years to drive further performance gains. And these larger models do better, but they require more compute and memory to be able to run. Now, it's common for ML researchers to release multiple versions of their state-of-the-art models alongside the flagship model of different sizes. And here we take the efficient detector family of object detection models as an example, which have model sizes ranging from ED0 at the smallest up to ED7 as their flagship model. And benchmarking their runtimes on the best available on-car GPUs compared to an H100 in the cloud, we find a very large runtime gap that quickly grows beyond reasonable runtime targets for on-car models. So as a result, only the smallest two of this family of models, ED0 and ED1, can run successfully within a target SLO. And this matters because these restrictions translate directly to decreased system performance. So here we see a frame captured by a Waymo vehicle from a front-facing camera. And zooming in on this frame, we can see that there's 4 cars there, 2 closer, 2 further away, and a pedestrian on the right. When we run this image through the actual ED models, we see that ED1 only detects those 2 vehicles on the left, misses the 2 vehicles in the back, and more importantly, misses the pedestrian on the right, who slightly blends into the background. Whereas ED7, the largest of the models, detects 3 of the 4 cars, and importantly, detects the pedestrian. So what can we do about this? Well, for some important context on the bigger picture, I'll go over the structure of these autonomous vehicle control planes today. AVs collect many gigabits per second of data, typically having a dozen plus cameras, a handful of LiDAR sensors, GPS, microphones, etc. And this data is then fed through a number of stages, starting from perception and localization, where we figure out what the objects in the scene are and where they are. Then to prediction, where we predict how those actors are going to move. Planning, where the car is going to decide its own trajectory in space, and control, where it actuates that trajectory. Now, in order to operate safely, the car must react within a very limited real-time SLO, roughly matching human performance and human reaction times on the order of 1/3 of a second to a second. And then zooming into one of these stages, here the perception stage, we can see that the control pipeline is implemented as a compound AI system. It's a DAG of services, like these object detection services that run on each stream of the camera feeds, and run in parallel, producing bounding boxes that are then passed forward onto and through environment fusion and prediction. And while the exact latency targets are kind of proprietary and kept hidden by the companies, prior work estimates the SLOs for this object detection to be somewhere around 150 milliseconds. Now, coming back to our original problem, let's look at the simplified AV control plane with this diagram in the bottom right. This car has two cameras, and for the control plane, we're going to focus on just the 2 object detection services for these 2 cameras, omitting the later stages. Our original problem was that only these small models, ED1, are able to run on the on-car GPU within the target SLO of 150 milliseconds. Now, a natural solution might be to turn to the cloud. And the cloud does offer us access to as many powerful GPUs as we need, but there's a crucial challenge, which is to get there, we have to traverse cellular networks. And these networks have high ping latencies, very limited and variable bandwidth, and can be highly unreliable, which leads to missed deadlines and safety risks. And simply the volume of data alone collected by the car makes it infeasible to just move the control plane entirely to the cloud. To solve this problem, we consider selectively offloading a subset of the services that can make it to the cloud in time, which is effectively pooling together our bandwidth for some specific services to get a chance to go and use cloud resources. Now, we observe that for any single service, the end-to-end runtime of offloading to the cloud is the current ping latency, plus the propagation latency, or the time it takes to put the inputs onto the wire, plus the runtime of the model in the cloud. And looking at typical 5G cellular conditions reported in past measurement papers, and benchmarks that we ran ourselves on how long these models take to run in the cloud, we actually see that it becomes feasible to do so, to take some particular models and make it to the cloud and back in time. But in order to do this, we have to
configure our selections very intentionally. We have control over the models that we choose to run and control over the way that we allocate bandwidth to a service and which service we give more bandwidth to. This raises the key question that our work addresses, which is we have to decide which services we're going to offload and which models we're going to choose for them to be able to run in the cloud. Allocating bandwidth to a service translates to giving it more cloud runtime budget, which allows it to run a larger, more accurate model. Now, there's many different possibilities. We could, in this case, in this example, share the bandwidth equally, and perhaps that enables both of our services here to step up to ED4. Or we might share the bandwidth unequally and perhaps give camera 1 more bandwidth, thus allowing it to reach the cloud faster and run a larger model. Or maybe we even give camera 1 all of the bandwidth so that it can run the largest model, ED7, and leave camera 2 having its model running on the car, ED1. So the intuition is for how we should decide this is that different services might benefit different amounts from getting to run on these cloud models. So the approach that we take in our work of solving this problem is to extend the idea of utility curves to encode these trade-offs and benefit, and then to use that to do our bandwidth allocation and model selection. So more concretely, we start off offline by benchmarking each model's performance for each service using data that was collected prior. In our paper, we use the Waymo open data set for this benchmarking, with the benchmark being mean average precision, which is standard in the object detection literature. And I'll note here, we collect both the runtime and the accuracy experienced by that service for that model. And then next, we construct a utility curve for each model of that service independently. And this curve captures the benefit to the car, namely accuracy, for a given bandwidth allocation. And I'll note, you can see here, this ends up being a single step function, because if not given enough bandwidth, that model simply can't finish running in time to return a result. So it provides no benefit to the car. And as soon as you cross the threshold of there being enough bandwidth given to leave enough time to run, then the model provides some amount of bandwidth, namely its accuracy, some amount of utility, namely its accuracy. And then we aggregate these utility curves into a separate, into a complete service level aggregate curve, which captures the benefit to that service of allocating additional units of bandwidth. Now, finally, at runtime, we will jointly allocate bandwidth and select our cloud models according to what maximizes the average service utility across all of these services, which we formulate as an ILP that gets solved. I'll note then also that to maintain safety, for the case where the car gets disconnected or network conditions suddenly change, we always run the on-car model as fallback, and we opportunistically use the cloud results that are returned. Okay, so in the paper, we go into much more detail about the tricks needed to make this work. One problem we ran into is that naive model options simply require too much bandwidth to be practical with one service, let alone multiple, which resulted in virtually no benefit below 170 megabits per second. There's a bunch of tricks we use to help with this, including adding compression as an option, which adds local runtime and lowers accuracy on the cloud, but saves bandwidth. And allowing the option to run preprocessing on the car, which saves some bandwidth but adds local compute time. So we can see as a result, our final utility curves had many more step-up points at much lower bandwidths, effectively pulling kind of the curves to the left, adding more benefit at lower bandwidths. Now, in order to evaluate Turbo, we applied this method for deriving service utility curves for the efficient detector family of models on the open source Waymo data. And we implemented our ILP formulation of our optimization problem in Python and built out the Turbo control module and the Turbo client and server in both Python and Rust. And we ran our evaluation both in simulation, using pre-recorded data from Waymo, and in a real-world deployment, testing on a modified real car. Now, for our simulations, we ran them on this Waymo collected data set of 100,000 scenes of 20 seconds each, which provided 5 cameras, their video streams, with ground truth labels annotated by humans. And we constructed our control system to comprise 5 detection services and 1 planning service. And what we found as we swept the space of 5G cellular network conditions reported in prior works was that Turbo improves the average accuracy by up to a full 15.6 percentage points. And looking in the range of kind of very typical 5G conditions, a full 10 percentage points or more. In the paper, we break this down further to show the factor analysis of which components of our design contribute to this result. I want to note that this is a great result because in the ML literature, even increasing accuracy by a few percentage points becomes a big result and makes for a new state-of-the-art model. Then to evaluate Turbo's practical real-world benefits, we ran an actual shadow deployment of Turbo. We outfit a real car with 3 cameras, a local server, a 5G hotspot, an antenna, and reserved and had a Google Cloud server and GPU running in a data center. And we conducted some test drives in Sunnyvale, running Turbo over a period of 2 hours of driving on the highways and on neighborhood roads. I'll note for safety reasons, we didn't allow Turbo's control plane to feed to any of the car controls, but we did take all of the live incoming data and processed it, either on car or in the cloud. And our results found that Turbo very effectively enforced bandwidth allocations under these changing network conditions and selected the right amounts of bandwidth to allocate to each service in a way that maximized the average model accuracy boost. And we saw that the actual model accuracy boost experienced closely matched the expected accuracy boost that Turbo expected by its allocations. In the paper, we further report performance micro benchmarks that we recorded during our drive, showing the performance of our system. Now, we discuss many additional details in the paper that I don't have time to talk about now, including Turbo's economic feasibility, the benefit of deriving these utility curves dynamically and techniques for doing so, system micro benchmarks, and more. I encourage you to see the paper for those. But in closing, we've seen that the cloud edge GPU performance gap is just continuing to grow, and that cellular networks are a very real challenge for edge systems to try to use the cloud. And in this work, we presented Turbo, which is our system for real-time utility-aware bandwidth allocation that enables AVs to use the cloud. And it does this in a way that maintains safety, opportunistically maximizes performance, while minimizing the cost of network and cloud use. With that, thanks for your time, and I'll be happy to take any questions over email. You can reach me at akrenzel@berkeley.edu. Thanks.
Okay, any comments from the general audience?
Professor Tuscher, please. Yeah, I really liked the work. It's a nice systems project. And I understand, I mean, also the benefits and they're doing the cloud-based inference optimistically. I'm just a little curious about real-world deployment, because I mean, this is an area that's heavily regulated and certifications needed to broadcast the work. You always have to plan for the worst case, right? So that there's no connectivity. So I just wonder how car manufacturers will deal with this. So that should be a lot easier to just plan everything totally autonomously and don't rely on the cloud. I mean, the work is great, but I just I'm curious how this could play out.
So I think that I mentioned that they continue to run
all of the models locally as well. Yeah. For safety purposes. Yeah. I'm sure there's an explanation for this which I missed, but I have to respect the question what benefits of what so the regulatory purposes, let's say,
But I think I find another case. I work on something trying to decode Wi-Fi on it, which might be useful if the local chicken adapter has some data. In the current situation, I agree with what you said that regulation might be a serious concern in the environment. But there may be other risks to this question.
Yeah, I suppose it would maybe not be the driving element because by definition, the autonomous facilities need to be dimensioned for all situations.
Right.
But maybe there are some other tasks. For example, you might have some gaming, whatever, happening in the car by some interactive screens that produce.
Or let's say you're using like a car, right? And it's an agent finds something that is car going out, and local chicken operators in the wall. You can send it to the cloud.
I mean, also, I mean, there would, I guess, there will be some, performance chips that we use.
But again, it's still there, right?
Gap is obviously.
But what is difficult to show is that in certain scenarios, safety is improved by what?
But that's hard to quantify.
I know, I've got an experimental idea. To simulate lots of crashes.
Okay, great. Then maybe we can move to the next video. Oh, it's already there. This actually is in our voting list, right? Syrian technology.
Yeah, that's but you could just go ahead.
Right. So the next paper after the voting result in the morning was who holds the steering wheel and the opacity and the consolidation in a CBN replica selection. The authors are from Northwestern and Idigo here. So let's take a look at what the authors are doing here.
I'm Rashna Kumar, a final year PhD candidate at Northwestern University. Today, I'm presenting our work, Who Holds the Steering Wheel? Opacity and Consolidation in CDN Replica Selection. This is a joint work with my advisor Fabian and collaborator Marcel. In this talk, I'll show how we can infer any CDN's replica selection mechanism without privileged access using latency fingerprints and what we learn when we apply our methodology at scale. Web content is increasingly served through CDN replicas hosted around the world. Replica selection is one of the quiet control planes of the internet. It determines where traffic goes, what latency users see, and how failures propagate. Yet, the decision process is almost entirely opaque to outsiders. We ask a simple question: who is actually steering user traffic, and how concentrated is that control? Our goal is to make steering observable from the outside without privileged access and without cooperation from CDNs. CDNs, which host most of the web, steer requests using internal policies we don't see. But the consequences are very visible, such as traffic localization, failure behavior, and jurisdictional exposure. There's also a structural wrinkle. Resolver geography can distort where users are mapped, meaning the entity influencing replacement may not be the user at all. Prior work has mostly evaluated performance. We focus on something more fundamental: deployment reality. How steering is actually implemented at internet scale. Our key idea is straightforward. DNS steering mechanisms leave distinct latency fingerprints. So, we resolve the same content through resolvers placed at multiple geographic scopes. Measure the RTT to the assigned replicas and compare the resulting distributions. Those differences let us infer the strategy: DNS-based, IP anycast, or regional anycast, without privileged access and at scale. For DNS-based steering, we expect distributions to separate strongly as resolver scope changes, because the selected replica changes with resolver location. For IP anycast, distributions should look very similar, because the same anycast IP leads to the nearest instance regardless of the resolver used. Regional anycast should match IP anycast within a region and DNS-based steering across regions. To test this idea in the real world, we run a simple controlled experiment. We use RIPE Atlas probes as fixed end-user clients spread across many networks and countries. For each probe, we resolve the same domain through 5 DNS resolvers at increasing geographic scopes, from local to far. For each resolution, we record the replica the CDN returns, and we measure the RTT from the probe to the replica. Because the client stays fixed and only the resolver changes, any systematic shift in RTT across scopes reflects this steering mechanism. Then we compare the RTT distributions across scopes to infer how the CDN is steering. Once we have these RTT distributions across resolver scopes, we need a compact way to summarize the pattern and classify it. That is what we call CRV. CRV is a 4-element vector, measuring how different the RTT distribution is between the local resolver and a further resolver scope, where CRVI is computed as the KS distance between the latency CDF from the local resolver and that from the I+1th resolver scope. CRV1 and CRV3 capture inter-country, that is local versus same region, and inter-regional variation, that is local versus far region, the strongest signals for distinguishing strategies. The patterns line up with the intuition from before. For DNS-based steering, the distribution changes a lot across scopes, so CRV values are high. For anycast, they barely change, so CRV values are low. For regional anycast, they stay low within region, but jump when you cross regions. So CRV gives us a simple signal that lets us classify steering at scale. Before measuring the ecosystem, we validated our methodology against CDNs whose strategies are well understood. Akamai shows the expected DNS pattern, Cloudflare collapses towards 0, classic anycast. Edgio falls in between, aligning with regional anycast behavior, that is low within region, high across regions. All correctly identified, so the fingerprint holds. With that validation in place, we scale up to measure steering in the wild. We run our measurements across the top 1,000 sites in each of 19 countries, covering about 66% of internet users. Using the same pipeline, we classify the steering behavior of 17 CDNs. And importantly, our vantage points span 6 regions. So this is not biased to one part of the world. With this scope, we can now ask what steering strategies dominate globally and how that varies by region. Now, to the first global takeaway. DNS-based steering dominates. Across our dataset, 12 of the 17 CDNs use DNS-based redirection, and DNS-based CDNs dominate overall prevalence and delivered bytes. Regionally, DNS-based is the most common strategy almost everywhere, except Europe, where Anycast is more common. DNS-based steering dominates overall, but some CDNs use more than one mechanism. Google is a clear example. Across Google resources, we see a roughly even split between DNS-based steering and IP Anycast. So steering is not one strategy per CDN. It can vary across services within the same provider. And that raises the question, is this hybrid model the direction CDNs are moving toward? To close, the key takeaways are this. Replica selection is hidden, but it shapes outcomes. We make steering observable with unprivileged latency fingerprints, and at scale, we see DNS-based steering still dominates, with regional variation and mixed strategies in large CDNs. As DNS resolvers consolidate, influence over steering concentrates, raising questions of resilience, sovereignty, and control. This work makes those questions measurable at internet scale. Thank you.
Okay, so I guess this will be the last talk in this session. Any questions from the audience? You can discuss for around 7-8 minutes.
Very generous. I like that the sort of theme of the day is consolidation, centralization. Yeah. Because that was also including points for this presentation too.
This work
Yeah, I mean, it's well understood that this is a really big problem. Right? So the mechanisms that we are using, you can call them like a hack test, right? So the DNS, especially the DNS-based steering. I constantly get complaints at home because I'm using DNS, DNS to some secure resolver. So I'm not using, where is it? It's fine. I'm not using the ISP one. This makes every Netflix interaction much slower. I'm not sure who's using the website. You can really tell the service would be at home to some complaints. And just you're not architecture has evolved over time. I think this is why like DNS zero came about because resolvers were getting used and it was screwing around with the DNS strategies with about CDNs. So, I guess also that points back to our centralization debate today. Because these third parties essentially consolidate everybody's initiative. There's a lot of ISPs that just by the HCP figuring to use third party resolvers because it offloads load and it's responsible for managing those services. That's true. And it's one of those surprising hidden problems in the network that people don't realize because the ISP focuses on the network itself. You forget that if you do a third party resolver, and all of the CDNs think that they're situated in California. There's a ton of transit. Super expensive. Like a few years ago, we did this study of CDN redirection strategies in Africa. And Africa's already got problems with infrastructure because a lot of this boomerang routing takes place where they exclusively use transit. We don't have really any peer agreements between their neighbours, so everything gets boomerang to say Paris and Amsterdam or London. But then as a double whammy, what they then do is they get everything to use third-party resolver in the US. Yeah, so you've got the boomerang effect of the routing plus the fact that you're taking all of your CDN traffic in America. Right. Yeah.
important stuff, improving network operations.
Like maybe the city governments are not able to deploy, or did they have an incentive to do that?
I remember it was in the ITF like Alto, wasn't it called?
Yeah.
So there was this effort in the ITF to standardize an interface between ISPs and content delivery networks, so that there could be some information exchange for steering traffic.
But why would the city have the incentive to do that? Actually, I don't understand.
Well, I mean, there's a lot of interaction already that happened between the CDNs and the ISPs. So, for example, when CDNs situate their infrastructure within the network operators themselves. And it's in the interest of the CDNs to provide as good a quality of service as possible to users, because that's what attracts customers to come and host on their path. So if Alto results in some very important for the CDN, possibly ISP, everybody's a winner.
We trying to get more instances into the own network, into the website, let's say, for example, application software that needs to agree to this. So they give the permission to get one more box. So to be as people supposed to offload the traffic and also postpone infrastructure extension by just adding more.
Yeah, I think a lot of big CDN players have some fairly public, clear criteria where they say, if you've got this amount of traffic, that's enough for us to deploy a box into your infrastructure. But I think for a while, ISPs were also trying to move up the value chain. So by bringing, let's say, cloud infrastructure into their own ISP, they felt they could make more money because the revenue you get from the traffic per bit is going down and down and down. I don't think I ever really took off in practice.
Okay, great. So if there are no more questions from the audience, great. So maybe just conclude this session and have a break.
Okay, so at this point, we're closing the pod. We've had a fantastic day, and it's now continuing in a more informal setting as the collective here heading off for a drink. So thank you to Zilly for organising.
Thank you to and Dirk as well.
And thank you to all of the hosts, the presenters, and the people participating in the lively discussions today. Hope everybody else enjoys their respective pods around the world. Bye-bye.